आशुतोष सर, सर ने फरी एक बार फोन कर दो सर.
હા સર.
કેમ કે સવાર પછી નહીં તો ડીલે થશે.
યસ યસ.
सर आपका स्वागत है सर.
नमस्कार, गुड मॉर्निंग.
नमस्कार, मैं प्रोफेसर विशाल दोषी, हेड ऑफ इलेक्ट्रिकल इंजीनियरिंग डिपार्टमेंट एट गवर्नमेंट इंजीनियरिंग कॉलेज भरूच.
भरूच, ओके, वेरी नाइस.
सर कई साल पहले मैंने ग्वालियर में एक आपका सेशन अटेंड किया था.
हाँ,
न्यूरल नेटवर्क पे था.
हाँ हाँ, लॉन्ग बैक. हाँ
हाँ हाँ. सर अभी प्रिंसिपल सर ज्वाइन हो रहे हैं, 2 मिनट लगेंगे, है ना, तो हम उसी की राह देख रहे हैं.
ठीक, नो इशू.
Dear participants and honorable chief guest, good morning to all of you. We are very soon we are going to start our program. Our respected principal sir is expected to join within few minutes, and due to some technical issues, there are some lag from his side, but very soon he is going to join. I think so. Sir has joined now. Hello, Joshi sir. Hello.
Yes, sir. हाँ.
I think so.
जोशी सर आ गए क्या? हाँ, आ गए. जोशी सर आ गए. जोशी सर आ गए हैं सर.
Okay. Joshi sir, kindly permit us to start the program. Hello. I think so. Some audio issue is there from his side.
Maybe.
Joshi sir, am I audible to you?
सर उनका म्यूट लग रहा है.
सर को ही शायद अनम्यूट. हाँ, yes, okay.
Yes.
Now.
Good morning, sir.
Am I audible now?
Yes, sir. Now you are audible.
Yeah, thank you.
Kindly permit us to start the program, sir.
Yeah, please.
Okay, thank you, sir. Thank you very much. Now, today we have a very distinguished guest, Dr. S.N. Singh, sir, with us. Good morning to one and all. I feel extremely honored to introduce the dignitaries present here. Honorable Chief Guest of the occasion, respected Dr. Srinivas Singh, sir, Senior Professor, Electrical Engineering Department, IIT Kanpur, and former Vice Chancellor, Madan Mohan Malviya University of Technology, Gorakhpur, UP. Respected Professor Dr. Sanjay Joshi, sir, who is Principal of the Government Engineering College, Bharuch. Respected Professor Vishal Doshi, sir, Head of the Department, GEC Bharuch. Respected Head of the other departments, GEC Bharuch. Dear faculty members, participants across the states of India who have registered to participate in this FDP. It's my pleasure to welcome you all on behalf of organizing team of this Atal FDP. I would like to introduce first our chief guest. He is very iconic personality in electrical engineering field, not only in India, but across the world. Professor Dr. Srinivas Singh, sir. He is very senior professor at IIT Kanpur. Just I would like to introduce, though he is not required any introduction to participants, he is well-known personality in the technical community of electrical engineering, but still I am reading few lines, not sufficient lines, but I am taken some lines. Professor S.N. Singh sir obtained his MTech and PhD degree in electrical engineering from Indian Institute of Technology Kanpur in 89 and 95 respectively. Presently, he is professor in higher academic grade, Department of Electrical Engineering, IIT Kanpur. Before joining IIT Kanpur as associate professor, Dr. Singh worked with UP State Electricity Board as assistant engineer from 88 to 96. And IIT Roorkee as an assistant professor from 96 to 2000. And with the Asian Institute of Technology, Bangkok, Thailand, as assistant professor from 2001 to 2002. He was vice chancellor of Madan Mohan Malviya University of Technology, very reputed university from the Purvanchal zone, Gorakhpur, during 2017 to July 2020. Dr. Singh received several awards, including Young Engineer Award 2000 of Indian National Academy of Engineering, Khosla Research Award of IIT Roorkee, and Young Engineer Award of CBIP New Delhi, India in 1996. Professor Singh is recipient of Humboldt Fellowship of Germany 2005 and 2007 and Otto Monstedt Fellowship of Denmark 2009 to 10. Professor Singh became first Asian to receive 2013 IEEE Educational Activity Board Meritorious Achievement Award in Continuing Education. He is also recipient of INAE Outstanding Teacher Award in 2016 and IEEE Region 10 Asia Pacific Outstanding Volunteer Award in 2016. Dr. Singh is appointed as IEEE Distinguished Lecturer of Power and Energy Society from 19 and Industry Application Society for 19-20-21. He is also recipient of NPSC 2020 Academic Excellence Award and 2021 IEEE Industry Application Society Outstanding Educator Mentor Award. His research interest includes power system restructuring, facts, power system optimization and control, security analysis, wind power, etc.
Okay.
Professor Singh has published more than 500 papers, more than 11,000 citations in international, national journals, conferences, and supervised almost 36 PhDs. 11 PhDs is still under progress. He has also written 30 book chapters, 8 edited books, and 2 textbooks, one on electric power generation, transmission and distribution, and second is Basic Electrical Engineering, published by PHI India. Professor Singh has completed 36 technical projects in India and abroad. His 2 NPTEL video lectures on HVDC transmission and power system operation and control are very popular. Professor Singh was chairman IEEE UP section for 13-14, IEEE Region 10 Asia Pacific Conference and Technical Seminar Coordination 15-18 and Region 10 Vice Chair of IEEE Technical Activities 19 and 20. Presently, Professor Singh is immediate past chairman of IEEE India Council. Dr. Singh is fellow of IEEE, IET, INAE, IE, IETE and ABH. The journey of Professor Singh is still continuing. His academic contribution is outstanding and inspirational to all the participants, including us. I personally had got an opportunity to interact with Dr. Singh at SVNIT Surat during his visit when he was Vice Chancellor of MMUT. Thank you so much, sir, for accepting and joining us. Now I would like to introduce my respected principal, Dr. Sanjay Joshi, sir. Dr. Joshi, sir, has completed his doctorate degree from the prestigious Electrical Engineering Department, IIT Bombay in 10. Currently, Dr. Joshi, sir, is serving Government Engineering College, Bharuch as a principal since 2020. Dr. Joshi, sir, is also Associate Dean, Gujarat Technological University, Ahmedabad. Dr. Joshi, sir, has also held the full-time principal position at Government Engineering Colleges, Valsad and Surat. during 14 to 2020. Dr. Joshi sir has also served as Chairman Board of Studies at GTU. He has qualified the Gujarat State Public Service Commission exam 4 times in his academic career. Dr. Joshi sir has published research articles in various reputed IEEE journals such as IEEE Transactions on Power System and IIT journals, Willy publications, etc. Sir has also served in various committees formed by Commissionerate of Technical Education, Gandhinagar. Dr. Joshi sir has motivated many faculty members like me towards joining the PhD program in his career. At administrative level, sir has initiated many technical activities at various colleges, particularly GC Valsad, Surat, now at GC Bharuch, for improving the quality of technical education. Thank you, sir, for joining, and in fact, we are very lucky to have you as a principal of this institute. You are always motivated and groomed the young faculty members across the various government engineering colleges of Gujarat. Thank you very much, sir, for your motivation and commitment of the technical education. Now I would like to introduce Professor B.Y. Doshi sir, Head of Department Electrical Engineering. Professor Doshi sir has completed his master degree from the LD College of Engineering, Ahmedabad in 2008. Sir has qualified the GPSC exam in 1999 and became assistant professor at LD College of Morbi in 1999. He became associate professor in 2010 at GC Bharuch. Sir has more than 20 years of academic experience. Sir holds the position of SSIP coordinator, GC Bharuch. Sir has also served at various capacities in GC Bharuch. Working culture of the electrical department has been very lucid and conducive since so many years. The full credit goes to Professor Doshi sir. He has always motivated and provided the moral support to all the faculty members in their every academic efforts. Now I would like to share a few things about our program. The motto of this program: the importance of renewable energy based mini and micro power system and its reliable operation has increased many-fold in the prevailing health of the global environment. The power quality issues are needed to be taken care for such systems where most of the energy sources are intermittent in nature. There may be various possibilities of microgrid configuration and its control. Therefore, this program aims to create awareness among teachers, industry persons about better utilization of distributed power sources, basically based on renewable energy generation system. The focus on energy efficiency and power flow control using various control techniques will be the additional feature of this FDP. Best possible combination of experts from various IITs and NITs have been invited to deliver the session apart from sessions from our internal experts. I hope all participants will learn certain new things and make it big in their applied research domain. Now I would like to invite Professor Doshi sir for sharing his words with us.
थैंक यू आशुतोष, आपने कुछ बाकी रखा नहीं है बोलने को, फिर भी सिंह साहब आपका स्वागत है और आप यहाँ जीसी भरूच से जुड़े इसलिए मैं अपने कृतज्ञता अभिव्यक्त करता हूँ। जोशी सर प्रिंसिपल जीसी भरूच का स्वागत है। सभी हेड, सभी कलीग्स, फैकल्टी, साथी, सहयोगी, सभी तालीमार्थी, सभी का स्वागत है ना। एक सर आपके साथ मेरा मेमोरी जुड़ा हुआ है। जब मैं वहाँ पे था ग्वालियर में, मैंने एक सेशन आपका भरा था, तब लोगों ने एक कमेंट की थी कि आपकी शकल और सर की शकल मिलती है ना। मैंने कहा था शकल में नकल है लेकिन अकल में नकल हो तो कुछ बनेगी बात, है ना। तो ये मेमोरी एक आपके साथ जुड़ी हुई है। अभी सर के बारे में इंट्रोडक्शन हुई है ना। सर बहुत बड़े आदमी है ना। और फिर प्रिंसिपल सर के बारे में जो कुछ बाकी रह गया है वो भी मैं पूरा कर देता हूँ। सर का पहला पहचान तो ये है कि सर प्रिंसिपल है, प्रिंसिपल सर जोशी सर। दूसरा पहचान जो रह गया है वो है कि सर एकमात्र ऐसे हैं मेरे ध्यान में कि जिसने 4 जीपीएससी पास किए। एक आदमी अपनी लाइफ में 4 जीपीएससी पास करता है। सर लेक्चरर डिप्लोमा से स्टार्ट करके प्रिंसिपल जीसी इंजीनियरिंग कॉलेज में प्रिंसिपल है आज। सर ने वलसाड़ से लेके भुज तक, वलसाड़ महाराष्ट्र के पास है, भुज पाकिस्तान के पास है, वहां तक हर एक एरिया में काम किया है सर। बहुत सी कमेटी में हेड है ना सर। सर के विचार का प्रभाव पूरे गुजरात पे पड़ता है ना, क्योंकि सर बहुत सी बड़ी बड़ी कमिटीज में है ना। अब मुझे ऐसा बोला गया था कि बाकी सबकी भी डिपार्टमेंट की पहचान करा देना, तो दूसरा मैं ही आता हूँ। तो सर ने मेरी पहचान दे दी, लेकिन मैं और एक पहचान मैं दिलाना चाहता हूँ मेरे खुद की, कि एक मशीन गर्म होता है तो आप सब काम करते हैं, लेकिन जब एक इंसान गर्म होता है तो क्या करना चाहिए, उस पर मैं काम कर रहा हूँ, है ना। इंसान, मशीन गर्म ही ना हो उस पर आप काम कर रहे हैं, इंसान गर्म ही ना हो उसके लिए मैं काम कर रहा हूँ। आप मशीन को मानव बनाना चाहते हैं, मैं मानवता डालना चाहता हूँ, है ना। आप बाहर का एटमॉस्फेयर शुद्ध हो जाए ऐसा वर्क करना चाहते हैं, मैं इंसान के अंदर का एटमॉस्फेयर क्लीन और शुद्ध और शांत हो जाए उस पे काम कर रहा हूँ, है ना। तो मेरा मेन रिसर्च एरिया मानव पे है, और मेरा एक सेशन फ्राइडे को सुबह को है स्ट्रेस मैनेजमेंट पे, है ना। पूरा मेरा खुद का रिसर्च है, स्ट्रेस क्या है वहां से लेके स्ट्रेस मैनेजमेंट में स्ट्रेस एलिमिनेशन, है ना। कुछ चीज है तो उसको मैनेज करना पड़ता है, लेकिन एलिमिनेट हो जाता है तो वो बात अलग बन जाती है। तो उस पे है, तो सब लोग को उसमें स्वागत है। दूसरा, ये कोऑर्डिनेटर साहब, गिरी साहब की पहचान दे, बहुत बड़े आदमी, वो भी बहुत ज्यादा प्रगति की है इस एज में और बहुत आगे जाने वाले हैं। ही इज अ राइजिंग स्टार, है ना। मेरे पास ऐसे 20 जेम्स है सर के साथ मिला के, प्रिंसिपल सर भी इलेक्ट्रिकल के हैं तो उसके साथ मिला के ये 20 जेम्स है, उसमें एक जेम्स है। बाकी जो को कोऑर्डिनेटर है ना, वो प्रशांत शाह सर है। ऐसी बिल्कुल ऐसी बात है कि जैसे एक माला होती है, उसके अंदर जो धागा होता है उसके बारे में कोई नहीं सोचता, है ना। वो सारे उसके मोती के बारे में ही सोचता है, लेकिन वो धागा ही सारे मोती का आधार होता है। तो इसी तरीके से प्रशांत सर ने भी बच्चों के लिए बहुत सारी ट्रेनिंग की, है ना। गिरी सर ने सबके लिए ट्रेनिंग की, और प्रशांत सर ने बच्चों के लिए बहुत सारी ट्रेनिंग की। तो प्रशांत सर का भी मैं स्वागत करता हूं और उसका भी आभार व्यक्त करता हूं। बाकी जो ऑर्गेनाइजिंग कमेटी है, अमी मैडम है, उर्वशी मैडम है, निकुंज सर है और दिव्येश सर है, सभी लोग की कोई ना कोई खासियत है, सभी की पहचान आपको मिल ही जाएंगी, क्योंकि वो 5 दिन तक आपके साथ रहने वाले हैं। तो अभी समय बहुत कम है ना। और मैं सिंह साहब को सब सुनना चाहते हैं, तो मैं आशुतोष से विनती करता हूं कि अपने कार्यक्रम को आगे बढ़ाए। धन्यवाद।
Thank you very much, sir. Thank you for your precious words. Now I would like to invite our respected principal, Dr. Joshi sir, to address and welcome our chief guest.
सर्वप्रथम एसएन सिंह सर को मेरे सादर वंदन।
प्लीज प्लीज, नमस्कार नमस्कार।
सर, मैं आपका तहे दिल से हार्दिक स्वागत करता हूं हमारे ये इनॉग्रल फंक्शन में। आप हमारे प्रोग्राम में ज्वाइन हुए, वही हमारे लिए बहुत बड़ी आदर की बात है सर। आपने हमें वो आदर दिया ज्वाइन होने के लिए और इनॉग्रेशन फंक्शन में ज्वाइन होने के लिए, और ये एफडीपी में एक एक्सपर्ट लेक्चर डिलीवर करने का भी आपने स्वीकार किया हमारे निमंत्रण को। उसके लिए मैं और आशुतोष गिरी और पूरी गवर्नमेंट इंजीनियरिंग कॉलेज भरूच आपके बहुत बहुत आभारी है सर। उसके लिए हम आपके बहुत बहुत आभारी है सर। थैंक यू सर। सर, गुजरात में टेक्निकल एजुकेशन में हम लोग अभी बहुत आगे तो नहीं बढ़े हैं सर, हम वो दिशा में हम जा रहे हैं सर। तो बहुत सारे कदम उठा रहे हैं हम, इसमें से एक कदम है ये एफडीपी का आयोजन। आप जैसे महानुभाव और अच्छे अच्छे एकेडमिशियंस और एआईसीटी हमको वो काम करने के लिए सपोर्ट कर रहे हैं, तो हमारा हौसला बहुत आगे बढ़ रहा है सर। तो हम आगे बढ़ना चाहते हैं, सभी फैकल्टी को हम मोटिवेट भी करते हैं सर, और हम चाहते हैं कि हमारा भी डेवलपमेंट काफ़ी हो, हम हमारे स्टूडेंट्स का काफ़ी एडवांटेज दे, उनका प्लेसमेंट अच्छा हो, वो भी एकेडमिक्स में काफ़ी आगे बढ़े। तो बहुत सारे कदम उठा रहे हैं, उनमें से ये एक कदम है। टेक्नोलॉजी के फ्रंट पे सर हम ये कहेंगे कि DER, डिस्ट्रीब्यूटेड एनर्जी रिसोर्स, ये दिशा में हम अभी बहुत ही काम हो रहा है। तो वो दिशा में काम करने के लिए बहुत सारे फैकल्टी आगे आ रहे हैं। इंडस्ट्री तो आगे गुजरात का जो रीजन है उसमें आ ही रही है, लेकिन हम ये सोचते हैं कि हमारा भी रोल है। तो काफ़ी कुछ रिसर्च इन द फॉर्म ऑफ पीएचडी हम चाहते हैं वो हो। तो इसलिए ये एफडीपी का आयोजन वो दृष्टि से हम कर रहे हैं जिससे कि जितने भी पार्टिसिपेंट हो उनको इसका बैकग्राउंड और काफ़ी जो रिसर्च चल रहा है अभी आज की तारीख में उनका भी उनको परिचय हो, ताकि वो लोग ये फील्ड में काम करने के लिए प्रोत्साहित हो। तो ये एफडीपी का आयोजन का हेतु ये है सर। बहुत सारे पार्टिसिपेंट्स हमको सपोर्ट कर रहे हैं ज्वाइन होने से, और हमारी गवर्नमेंट ऑफ गुजरात के जो डिपार्टमेंट है डायरेक्टरेट ऑफ टेक्निकल एजुकेशन, वो भी हमें सपोर्ट करते हैं बाय डेप्यूटिंग द फैकल्टी मेंबर्स फॉर 5 फुल डेज। तो हम उनके लिए सबके आभारी हैं। सर एक छोटी सी बात, हम मिले हैं आपसे सर आईआईटी बॉम्बे में, करीबन शायद 2008 में मिले थे हम, आप वहाँ पर आए थे। उस टाइम आप पीएसओसी के वीडियो लेक्चर्स भी आयोजित कर रहे थे सर अंडर एनपीटीईएल। तो हम आपसे बहुत प्रभावित हुए थे सर। हमने एक 1-to-1 हमने बात की थी सर। तो वो आज भी मुझे याद है। आप जैसे महानुभावों से मिलने से जो एक्सपोजर मिलता है, जो मोटिवेशन मिलता है, वो मुझे याद है। और जब भी मेरा कोई जूनियर मुझसे मिलता है तो मैं यही कोशिश करता हूँ कि वो उनको भी मैं मोटिवेट करूँ सर। यही मैं अपना फर्ज समझता हूँ सर। अगेन सर आप हमारे साथ जुड़े, वो हमारे लिए बहुत गर्व की बात है सर। आपको बहुत बहुत आभार, सादर वंदन सर।
धन्यवाद, थैंक यू।
जी सर। गिरी सर म्यूट, आपका माइक म्यूट है सर।
Hello. Yes. Thank you very much, Dr. Joshi sir, for motivating us and sharing your thought with Dr. Singh sir. And now I would like to invite Honorable Chief Guest Dr. Srinivas Singh sir for enlightening us with few words. Though next session is going to be taken by sir only, but during the inaugural function, we would like to listen you sir for few words, please.
Okay, good morning all the listener and viewers. I can see there is more than 90 people are attending this FDP program. And this program is a very, very relevant. So basically it is a thanks to the principal, head of department, and of course the organizer, GRI, and many, many more faculty members are involved to organize and to connect the people across our India. And I was just looking at the program, I was very impressed that all the stalwarts in this area, especially in the microgrid, the reliability, the power quality, they will be talking in this conference. Now already I was much appreciated by GRI or Doshi sir or Joshi sahab. No doubt I have met all of you. But only I say all my fellow colleagues, the commitment is very, very important. If you are committed, you should deliver. And I'm standing here, just so you know, my mother is in ICU. Just she admitted yesterday. But I didn't cancel the program. I said, okay, I'll manage and I'm going to deliver. So whatever you just said, it is basically try to deliver. Because any program, it was very easy, so I should have told, no, it is not possible for me. But you can see this whole, the people are, those are behind. So the being a teaching as a profession, our commitment is very, very important. Now coming to the topic, as you know, this is a topic, you may be expert in any of the area like power quality, reliability, microgrid, power system. You are knowing, but I can tell you, and yes, you can think, I'll give the same topic to all 100 people, those are attending here, just talk about the reliability, or talk about the power quality. And you'll find the 100th new version will be there. Why? It is, the topic is same, but the way of the presentation, way of thinking, way of explaining, and way of giving the information and the knowledge, the basket, it is a totally different. So whatever you are knowing, it is immaterial if you are listening anybody else. That's why we keep on listening others as well. And a good faculty member, or that is always we say you should be a good listener as well. And this is liking most of the academic programs or faculty members. They say, he's speaking, and I know this, I can read this. You never read. If you are having this attitude, you cannot never study all these things. Because if you're sitting in this maybe 1 hour or whatever the individual will be speaking, I can say you can have the ocean of the knowledge that you can get in that area. Because reading the book, it is possible, because nobody is talking from the sky. It has some basis. You can get those information. But the digging those information requires huge time. But just listen 1 hour, anyone, in any topic, I say, whatever, even though you are experiment, that certainly you will find there is a value addition in your knowledge. And if the value addition, that's why this program is there. Because you are the teacher, you know, it is expected you should know. No doubt this is a slightly advanced topic, maybe on the research oriented. It is not that it is you are not knowing. Many of you already are knowing. Many of you will be basically known by this program. So being a teacher, always we need to improve ourselves, our knowledge. And that's why it is said they are organizing. And already it was said that I will be speaking on this topic. Of course, I will be talking at the very fundamental of the microgrid, which is after this inaugural program. And you know this energy, because it is very fortunate that here in this inaugural function, all the people of electrical engineering, even though I'm studying the principal, of course, head will be electrical, the organizer will be electrical, and other people will be electrical. Those are listening, they are also electrical. And you know this energy is the key indicator of development of any nation. Right now, you can see the war which is happening in the Ukraine and Russia. It is also based on the energy. The person who is having energy, he is basically, and that is no doubt. I'm not talking only electrical energy, because electrical energy cannot be stored. It is generated from some other energy. It may be oil and gas, it may be nuclear, whatever you can say. So the energy is a very, very important factor for the development of any nation. And that you can say Middle East, why they are rich? Because due to that they are having oil and energy, the reserves. So the energy is the indicator, and the electrical energy is going to play a very vital and the green or clean energy in terms of the development of any nation. World is focusing that we can provide the energy. So here they are talking about once you are having more and more energy, then the many things are challenging, like the quality. Because we are using the power electronics devices, they are basically prone to the power quality issue, and they are going to pollute. Right now, this penetration is limited, but there is a possibility that is going to be more and more in the future. Then how to handle all these things? Reliability. We were going for the microgrid for improving the reliability, but it's small devices. Once you keep on integrating, if there is a fail, what will be the reliability? Whether you are going to get the reliable power, how much reliability you are improving by doing all these things in terms of distributed generation. We have to, because earlier I was knowing, even though I worked 8 years in the State Electricity Board of Uttar Pradesh, and I know even though I was in system planning, and we were writing the report, no, we cannot allow even those sugar mills to generate and inject the power to the grid, because we were thinking there will be the voltage stability, there will be a stability issue, and the system will be collapsed. But now you can say small 5 kilowatt or 10 kilowatts are also integrated to the grid. So that's, you can say, change in the philosophy, mindset, and the technology, of course. The technology has also come in the better way. So we are improving from all the time, and it's our whole electrical system is changing from the conventional, only you can say thermal power station, big transmission lines. And now you can say we were only relying on the synchronous generator, and then we were having the AC lines. Now what is happening? The DC is everywhere. So now DC generations, all the distributed generations, most of them, they are the DC. Like wind, if you are using permanent magnet synchronous generator, you are using fuel cells, you are using the solar, they are the basically DC. So generation is now going to be AC and DC. Transmission, you know, every time now we are connecting all these big HVDC lines. And now we are going for the small, also trapping the renewable energy sources with the voltage source converter based HVDC. And that is also going to 18 and DC. Coming to utilization side, earlier we were only thinking that's a standard bulb, later the CFL, now it is LED. And all your other appliances like your induction machine, now it is again the power electronics base. Your charger, your computer loads, they are DC loads. So many now the DC. So DC and AC is a mixture. And once it's a mixturing, problem starts. And that's why I hope this conference will be touching all those aspects. I was looking at the topics of the various speakers. They are touching almost. It is not possible that in 1 week that they will cover all, because each one is one book. Like power quality, people are teaching one complete semester. Reliability is teaching one complete semester. Even the microgrid and distributed generation, they are coming in one semester. So in 1 week, it is a condensed matter. It is expected you are having some certain background. some people will be talking from the very fundamental and also showing with the path for direction for your doing your research, or maybe other guidance of your fellow colleagues, or maybe your student. That will be very, very useful. So thank you very much for giving this opportunity for this Bharuch Government Engineering College. While the program was going, then I was looking very dislocated. I have heard this word very well. No doubt I passed through the Bharuch, of course, because I know Surat, I know Baroda. I visited even the Gandhinagar, even the Bhuj, and all the areas, Ahmedabad, no doubt. But then I was thinking, it is very near to the just between your Surat as well as the Baroda. The Bharuch is one part, and from there there's a Statue of Unity there. Even though this December I plan to visit, November, yeah, I plan to visit Gandhinagar because we are having Indo-German project to visit this Statue of Unity. But again, I could not go due to admission of my mother in the hospital. So I joined online. I could not visit because it was planned. Everything was there because we are having a Germany at that side collaborator in India from the IT Gandhinagar and me were there. But anyway, I'll visit your college also once COVID will be off, and try to see the Statue of Unity, which is a prime importance for our country. Thank you very much. Wish you all the best for your success of this conference. Thank you.
Thank you, sir. Thank you very much for sharing your valuable words and taking some time from your very, very busy schedule, sir. And now I would like to invite Professor P.K. Shah, co-coordinator of this program, for vote of thanks to all the participants as well as other fellows who have just who has to leave after this inaugural function.
Thank you, Dr. Asutosh Giri, sir. Our honorable respected chief guest, Dr. S.N. Singh, sir, senior professor IIT K and former VC MMUT VP. Our respected principal, Dr. S.R. Joshi, sir. Our respected head of the department, Professor Vishal Y. Doshi, sir. Our coordinators of this STP, Dr. A.K. Giri, sir. All the participants of this STTP, our faculty members, our organizing team of GC Bharuch, on behalf of GC Bharuch and STTP organizing team, it's my great pleasure to extend a vote of thanks to our respected chief guest, Dr. S.N. Singh, for sparing his valuable time and gracing this inaugural session by addressing the session with motivational words. I heartily thank our respected principal, Dr. S.R. Joshi, sir, Principal GC Bharuch, for his motivation and inspiring mentorship for such kind of events. He is a constant source of inspiration to all of us for such kind of events. He is motivating us throughout. My hearty and sincere thanks to our respected head of the department, Professor Vishal Y. Doshi, sir, for providing great support and help for management of this event. My sincere thanks to our STTP coordinator, Dr. A.K. Giri, sir, for his day and night hard work and passion to arrange this STTP. He has worked very hard to arrange the sessions of the very renowned experts throughout India, and that will help all the participants. I am sure that all the participants will enjoy and have a great knowledge throughout knowledge and experience during this period. My sincere thanks to Atal Academy, Atal AICT for sanctioning this STTP. My thanks to all the participants and faculty members of GC Bharuch and organization team of our GC Bharuch who had worked very hard for arranging this STTP. And last not the least, I thank all those who are directly or indirectly involved in organization of this STTP. Thank you everyone. Thank you very much.
Unmute, huh?
Thank you very much, Professor P.K. Shah, sir, for your continuous support. Now, participants, without any break, we are going to start our first session with Dr. Singh, sir. I hope so. You all will enjoy and will be enlightened with the words and technical expertise of Dr. Singh sir. Now, Dr. Singh sir.
Okay. Let me share my slide. Windows. Okay, I hope you can see my slide.
Yes, sir. Now it's coming.
Okay. Okay. So once again, good morning to all of you. I can see that there are approximately now the 100 people they are joining, and still they are joining for this program. And I am the first speaker of this course. Oh, it is moving. Oh, there was some time limit. Yes, I know. So it is. I'll be talking about the microgrid, its control and operation, because you can see this FDP is the power quality, and it is the reliability of the distributed generation, along with in the microgrid how they are going to be useful. So my talk will be this is smart multi-terminal DC microgrid control and the operation. I'll start with the very basic, and then finally I'll show me some of the works which we have done for your R&D purposes. The question always I start, why the microgrid? Why you need it? Whether it's really needed for this our system or not? Certainly it is needed. We all know very well that the microgrids are going to be very popular. Earlier we were talking the smart grid. Smart grid is not a microgrid, but a microgrid can be smart. So it is, we are just trying to understand what is the microgrid that is and why it is needed. As you know, there are the limited expansion of the transmission capacity, and this is just allow me. I want to change the timing of this because it is moving continuously. 1 minute, just give me. Animation. I can say no. I want to the animation, the timing. I want to know how to remove. I don't know. Anyway, I think let us go as it is. Okay. I'll try to go back. So I'll be talking about this. So first one already, you know why I was talking, why you need the microgrid. No doubt there is a limited capacity additions, and also the difficulty in the constructing new line, because the new line construction is not so easy due to the various regions. Various regions, as you know, if there may be your location is the far end, you are having let's suppose 1 or 2 villages, and suppose you are want to construct a transmission line, it is a very, very expensive affair. And also lines everywhere, whether it's going in the metros, cities, or in the rural areas, there's a getting land and getting a lot of other things. Those are basically one of the aspect that is one of the problems that is there. We are also a lot of problem in the setting large power generations here. That is the concern. So the direct connection of the renewable energy. So we are just going to focus on the renewable energy sources to utilize in the market or utilize in this energy system, but they are creating a lot of other problems such as voltage rise, frequency variations, protection issues, network contingencies, and more stress on the electrical network, etc. they are going to pose. Because the renewable energies are the nature dependent, but they are clean. And once they are clean, so it is always we are trying to focus on more and more renewable energy sources there. Therefore, the concept of microgrid is one of the solutions to integrate the mixture of the renewable energy sources, because we are having the variety of energy resources. It may be wind, it can be solar, it can be biogas, biomass. So all, even the fuel cells. So they are basically the combination. So yeah, they are small. And small means that is a distributed generation. So that's how they are going to fit in, especially where it is a very difficult to reach to get this grid supply, or having the very weak grid, which is basically connected. So in that, it is a very, very obvious that we can go for our countries, you know, this geographically how it is located. We are more concentrated on the metro cities than the remotely placed villas, people in the plain or the hilly area, just you can see this providing the electricity is very, very expensive and highly unreliable. So we can use the distributed energy resources for them. So that is one of the aspects that we are basically looking for, and the microgrid is going to be one of the solution for this. Renewable energy sources, you can say last few years, they are the fast develop. There is a fast development, and the deployment of the renewable energy sources have created increased interest because of various reasons. We know there's always our demand is increasing continuously, whether it's the lifestyle is changing of the individual, then we require the electricity. We have a lot of even the industrial development, lot of agriculture development, commercial growth. So everything has related to the growth of electricity. Once it is growing, electricity demand will be growing. And once they're growing, then we have to meet the demand. And this demand can be, we are meeting by the fossil fuels, which is again is one of the concern because there's a fast depletion of these resources, and also the price increase as escalation of these price has forced us, and the technological development in other areas like renewable energy sources. Earlier they were very expensive, and now they are very cheap compared to fossil fuel. So these all has forced us to think about the renewable energy sources. So limitation on the already earth fuel resources, but and also the environmental degradation. There is a protection issue, and our environment concern was also there. And also at the same time, the electricity market is emerging. If the market is there, always we are search for the cheaper electricity and the manage the electricity in a such a way that people can buy, and that you can make more business oriented basically it is there. So all these are basically related to the renewable energy sources, which is basically required. And these renewable energy sources are various distributed generations. Already this is the theme of this FDP, that is a wind turbine. It's connected to the wind farms and the wind resources where one turbine, maybe many turbines. So maybe the layers of farms are also available. Solar photovoltaic, we are having fuel cells, micro turbines, biogas. All these things are combination of small, the distributed generation. Those are going to be the importance in this aspect. So the advantage of the microgrid, I can say the emergence of the use of the renewable energy sources due to the reduction of the CO2 emission. We say the microgrid, if you are going to use, and you are going to use the renewable energy sources of the small contribution. If they are generating in the big farm, it can be directly connected to the grid. But if they are very, very small, connecting the grid will create a lot of other costs, associated transformation system, transmission line, other things. But if you can, these renewable energy sources are integrated in such a way that they can be utilized locally. And if they can be utilized locally, then we can improve the reliability of the system. We can improve the efficiency of the total system. We can improve the performance of the system. And also we can basically minimize the CO2 emission or greenhouse gases, basically that is also can be minimized. And these renewable energy sources, if using the microgrid, very easily they are connected at the operating voltage. Otherwise, what will happen? You require various converters, you require various transformation, and the cost is going to be further increased. That is one of the concern. So the answer to the energy crisis and more reliability, if you want to improve the reliability, then because if you are taking a weak interconnection, and that basically will be is one of the concern, especially in the rural area, because one line is going, and due to the various here and there, finally the supply to those areas is very much erratic and unreliable. So, but if you're having the renewable energy sources locally, and also sometimes you can have something other along with the storage devices, other thing, you can very reliably, you can maintain them. So that is the energy crisis in those area. That's if you're utilizing so renewable energy sources, and that's why our government of India's main focus to go for the solar energy as well as the wind, because wind almost we have saturated because our sea is very deep, not shallow like European. But in the land side, onshore, you can find a lot of wind turbines are basically operating, and that's very huge as well. And the solar is now going to be booming because we believe that we are having the 300 clear sky days in 365 days in the year, and that is basically potential of the India, and that's the government is trying to add. And you will see every month we are adding at least 10 to 15 megawatt by solar, and government's mission is a very heavy in 2030 that we have to go for more than 400 gigawatt or so by the solar itself. So that is coming all the way to our meeting our energy crisis and giving the more and more reliability. So higher flexibility and the controllability. If you're having microgrid, very easily you can control. That's when you require the loads, when you require not, because depending upon the available resources, you can control locally. Because if you are controlling in the grid, it's very, very difficult, because the grid, the frequency, suppose you are 5 kilowatt turning on and off, it will not change, because that's inertia is very high, very big players are there, very big generators are there, they normally controlling, and that control is another aspect. So if you are having a small microgrid, you can with the help of power electronics devices, you can control them. It also reduces the T&D requirement, already I said, and the transmission losses in the system. As I said, the transmission loss, if you're moving in the several kilometers from the main substation and the power is going, huge loss in this transmission system. But if you can generate locally and utilize locally, this loss will be reduced, and the requirement of the transmission and distribution network may be also reduced accordingly. So that is another, depending on the case to case. And that's why we say it is a higher efficiency of operation you can achieve in the microgrid, because your efficiency you can improve and you can control in a very smooth and flexible way. The efficiency of the operation can be increased. The bidirectional power flow between the microgrid and utility grid, you may have the utility grid together. You may have the weak interconnection. Suppose that at any time you are having more power, then you can bank it. You can send it to the utility grid, and the ones you require more, you can use as well. So that's, you can have the bidirectional flow from the microgrid as well. In case of you are having the enough generation, then you can send it to grid, and when you are having shortage of generation, you can get it. As we know, the load variation of any grid or any load or any house, you will see it is a varying throughout the 24 hours depending on the usage pattern, and that we know because our demand sometimes more, sometimes less. So that is, if you are connecting with the utility grid, even though weak here, but still if there is some problem, then microgrid can be manage and we can supply the critical loads. And if you are having the storage system, of course, I can say you can autonomously you can control microgrid and you can improve the efficiency of that. Extra power can be sold to the utility grid. I already said that we are connected, then you can sell it, and then you can make the richer as well. You can make money out of that if you are having the proper microgrid. Then, in case of grid failure, the microgrid can supply the assess the load under the grid connected mode. So if suppose there is a grid failure, the microgrid can supply the access load under the grid connected mode if connected. So they can also start, even though they can provide the ancillary services. And you know, the ancillary services means they can provide the voltage control, they can provide the frequency, even though they can provide the black start capability of the whole grid, because they can give some power, and based on that you can restart your auxiliary. Because if all the thermal power stations on hydro is backed up or they are out, then you have to start, and for that starting you require huge power. For thermal you require 10% of its capacity as auxiliary power, and you have to run for many hours to synchronize the grid, and that power from where you can get. So normally what we do, we use the DG sets at the hydropower stations, and because they require only 1% of the power for, even though to synchronize or to generate the power from hydro. My auxiliaries are very less in the hydro compared to the thermal. And that if you start hydro and then then you can charge the line, and finally you can reach to the other thermal power station where you can start the auxiliary power, and then you can slowly. So what you can do, you require, sometimes you require the 6 hours, 24 hours to complete the grid restoration if the really grid fail is there. So, but microgrid is there, we can provide the locally, we can charge the line, and then we can also provide some of the ancillary services at the time of blackout as well. So the lot of advantage of the microgrid, that's why it is a booming area and people are working, but we have to see what you need, what the control philosophy, how we are going to, people are working more and more, because we know these devices you can connect. Now the issue is the control philosophy. So there are a lot of challenges in the microgrid implementation. It is basically related to whether you want the AC microgrid or the DC microgrid, because both are having its own advantages and disadvantages. Because the DC is, it is a various advantages, as you know. DC, you can control the power very easily. In the AC, it is very difficult to control. You can have the DC where the various losses are minimum. AC, the losses are more, and many others like reactive power and other things are coming into the picture. So it was found that the DC is the better option, but if you are already having AC system, changing and then putting further DC, that is another expensive affair. So it is better that it is decided if you are going for the new microgrid, you can go for the DC. Only the problem in the DC, that's the protection system that you have to do. So that's is one concern. In AC, the protection is very easy, and that is you can use any relay, that is possible. But the lower voltage, the DC protection, that you can use the converters for the protection system as well, and it is possible. And because microgrid, we always think about the lower voltage, and as well the lower power capacity of that grid. So the AC and DC, which one is choosing, it all depends upon the scenario what you are having at the existing one and where you want to move. And even the people are saying the DC is the better, of course, many aspects. But even the people are saying it's not microgrid. Why not? We can go for the picogrid. Suppose you want to have a grid in your house, picogrid or nanogrid, because that is in also you are having many load points, many your wires are moving, and various voltage level you require. Charging for your UPS is a different, charging for your mobile is different, voltage required, charging for your computers are different. So it is a possible that we can have the different voltage in the one house and then we can use the DC completely. Again, this is another concern, but that is also people are thinking and making system more autonomous, your household as well. Another is if you have decided AC or DC, then you have to decide the control philosophy. Which generator is going to control voltage? Which generator is going to control the power? And thereby maybe AC then frequency. So that is the control philosophy of whole system must be designed properly so that you can improve the reliability, you can improve the quality. All the things are related, then control philosophy should be done. Various researchers have given the various type of control philosophy. But this microgrid is also related to the more business oriented. You know, just here in the near to Kanpur, there is a one city one now. Although it's very popular in some sort of the earlier one, MLA has did something. But this I found some German companies are there in the villas, and they were basically giving earlier the power to the villas, and they were giving the charging, and basically they were generating by solar, and they were giving the light to them in the night when it was not connected, especially with the grid. So many villages where the people were paying for the charging their mobile, lighting, and the simple loads were given only light and fan and the charging points to them, and they were charging. So it is also the huge business is there. The business in terms of you can make the money, you can sell, you can generate, a lot of things that you can, basically it is a possible in that. But this is also more in business, it's going to increase if you are going more. Anyone can manage this small area in the house, and then the many people can be employed accordingly, and that revenue collection, other things can be done. So that is also the source of employment. Source of other things can be also done here. Another concern is a lot of data handling, and then if you're having the data, then this also in information security is one of the issue. Why? Because since they are generating, it is not just like there is the energy meter what they're consuming. Because sometimes the cost will be very high when the expensive generators you are using, sometimes less. So nowadays the data is recorded each node every time. And based on that, it is the price is shared. So the huge data is there. Also, once your data is there, then the concern is the data is moving to some center, a control center, you can say. Then there is a possibility of the security. Some people can hack, some people can manipulate, and many things they can do. Those are another issue of the information security. So the security, because sometimes they know your consumption pattern in the house sometimes is zero. The people may think, oh, nobody is there inside, even though some other illegal activities like robbery and other thing also can happen. Or people can destroy your system somewhere by the security. So it is a cyber physical system. Is there a lot of people are working in the cyber physical system, not only for the microgrid, for all over our power system, because that's one of the big concern, and that's why computer guys are coming forward for doing all these things, because we are having the data flow, we are having a lot of the missing of the data in the smart grid, and also many devices are on the IP, because I can from here I can turn off my whole this IIT Kanpur system, because we have from here turn on off. Suppose anybody else is doing intentionally, then it is creating havoc. So that's the secure system we require, and that is one of the concern that is happening. Another is the cost-effective implementation of the ICTs. Like you have to, whatever the system you are applying, you are having the information and communication technology, that is a play, because you have to have the data, you have to have a communication system so that it easily can be assessed, and that without going manpower individually to individually house and asking that. So there's a cost-effective implementation in all the smart grid, whether it's a smart your microgrid, smart your distribution system, or smart transmission system. In that, these are the very important aspect as well. We have to see which is accurate, which is the best one, and which one is going to be cost effective, because the cost always, we engineers always talk about the minimum cost criteria for all our operation, control, and even the design as well. And that is also here, this ICT is required. Also, we require the forecasting. Why? Because once you are going for the renewable energy sources, they are the nature dependent. They are very difficult to control because they are known as these distributed energy sources as a non-dispatchable generator. Suppose any solar is generating its capacity less than 50%. You want to increase, you cannot. Why? Because you cannot change the irradiance because it's given by the nature. So that is the upper limit you cannot do. Lower you can do, you can reduce, that is possible. But the only halfway, only one-way control is possible, not two-way control. And that's why you require very fast accurate, because if you suppose there is a possibility right now the wind is very high at this moment, after 15 minutes it may be zero. And once it is zero, then what is going to happen? It's a very, very difficult task. It is a very, because you cannot have a thermal, you have to start thermal restarting require 3-4 hours, or maybe at the grid is not possible. So many things, if you are having the accurate forecasting, then you can manage your grid, microgrid in the further 24 hours in the very efficient way. So nowadays, this accurate forecasting, a lot of people are doing the forecasting for solar, wind, and also the various, like even the people are talking about the price. They are talking about the ancillary services. So the forecasting earlier we were doing for the load only. And the load is also here required because you know what will be load is going to be next hour. You should be ready for that. So for the complete 24 hours, we require earlier we were doing only load forecasting. Now we are going for the price forecasting. We are going for solar forecasting. We are going for wind power forecasting. Which is required, and that's I can say it is an important aspect of that one. So the in microgrid, what are the things we are having? The microgrid, as I said, it is a small scale power supply. It basically provides the power to a small community. It's a few megawatt. It is not that you are going to 1,000 megawatt or 100 megawatt. It is not more than 10 megawatt capacity. Normally, it is talked about 1 to 2 megawatt that is needed. So in that, the microgrid may consist of components like you are having the distributed generations, including renewable energy sources. Why I'm saying because many distributed generations they are not renewable energy sources, especially if you are having the micro turbines, they are using gas. So it is basically that you are having completely renewable energy sources, or you can say distributed energy sources, that is a small capacity of generation unit ranging from 1 kilowatt to 10 megawatt and placed near to the load centers. They are known as the distributed generations. Can you see my slide?
Yes, sir. Okay. It is visible.
Yeah, okay, good. So this is the one, it's very important that you should have the renewable energy sources. And the many systems, we want that we should have some energy storage because if you are having the distributed sources, they are having renewable energy sources, so it's nature dependent, and your load is not matching exactly what the nature has given the energy at that time. So if you are having the energy storage system, that is also required due to the uncertainty and intermittent nature of the output of the wind turbine or solar DGs, and also we are having variable load demands. So if you are having the storage, it will be not connected with grid. Storage is very, very important because night solar is zero, wind may be there, not be there, and you require more demand. So normally we use the energy storage as well in the micro energy system. Now its specificity is how much. It all depends upon your loading pattern whole day, and also whether you are connected with the utility grid or not. If you are connected, then this storage system may be not required, or maybe the less amount of the energy storage system is required. So that is also a part of the microgrid. And of course, the power electronics converters and their controls are very, very important because all these devices are connected with the power electronics, and their control philosophy and other things are required. Your load may be your AC load and the DC load. I talked that we are having all the type of AC and DC loads, and you are required from a small distribution network as well because you are connecting several consumers together. So a small distribution network is also there. At the low voltage level, always we talk approximately 400 to less than 11 kV, or something depending on the DC and AC. So the microgrid can operate under the two modes. One is the islanded mode, means with no connection of the grid, and you are just operating. So that is a very challenging task where you require a lot of energy storage devices, along with that you can maintain the 24-hour electric grid for the end users. And that is the islanded mode's operation. If you're having the limited energy storage devices and you are having limited distributed energy resources, then always you will be in the start of the energy, which is you cannot meet the load demand. And that if you are not meeting the load demand, then you have to go for the load setting. You have to go for the critical load, only giving the power at the specially required period sometimes. So the islanded mode, if you are having sufficient, then you can go for the islanded with the storage devices. That is also good enough. But it is a grid connected mode. It is possible to connect the grid. It is easier and better for the reliability of the microgrid as well. And the surplus generated power can be transferred from the microgrid to utility grid, or the vice versa in case of the deficit, or it can be the increase in the load demand is there. So that's it again, depending on it is both type of microgrids are basically available in practice. There are a lot of opportunities of microgrids. This offers opportunity of the electrification in the remote areas, and that is one of the things, because if one village is very located, two villages, very small, even the rural areas are there. And that's basically the power has to go, and that it is there. So that is we can meet all these things. Defer the construction of new transmission lines. If we are generating more and more microgrids, so the transmission line requirement is also there, because once the power is increasing those area, then the transmission line and distribution line increases there. So that is also differing it. Creates the job opportunity. That's also another is in the niche area here. A lot of, as I said, is a business market, and you can have a lot of job creations that you can have in the microgrid. That should be also seen. It will reduce the dependency on the imported fuel, because you can locally and nature dependent energy. God has given a lot of energy to us, and if that can be utilized, that is better and better for the other things as well. So the microgrid can be classified as the AC microgrid, the DC microgrid, and so on and so forth. That is basically one of the concern. Already I was talking with the AC and DC, what type of the DC grid you are going. So the architecture of the AC microgrid, you can see here is a network where it is not that all the loads and generations are connected to one bus, but it is a small distribution network. Here is the low voltage that we can have the wind, we can have the solar, we can have the fuel cells, we can have the battery storage. So these are the basically generation here. This is basically both, you can say charging and discharging options is there. So you can say the double arrow is there, but these three are giving the power to this AC microgrid, and these are the various loads that is there. It can be the electric vehicle load, as you know, it's the DC load, so we require the low voltage from 400 kV. It is just we are taking 400 voltage basically, the three phase. So it is you require the transformation, then you require converter from AC to DC so that your electric vehicle can be charged. You can have the DC loads, and you can have telecom loads, lower voltage. And all these things, again, the converters are used. You can have directly single phase loads as well. You can have three phase load as well. So these are the various loading. And again, you may have connection with the utility grid or not. It depends all that's whether the islanded mode or if the grid connected. If it is there, then the switch will be closed, otherwise not. So now you are having generation, you are having this, and you have to manage the grid with utility grid and without utility grid. So that's who is controlling the voltage. Who is controlling the power balance here in all these loads are changing? So that is the battery is changing. So that is some philosophy. There's a control philosophy. When I can charge my battery, when can I start my fuel cells, and so on and so forth. So that basically you can say the varieties of the power electronics devices like converters everywhere. And that is a one architecture of AC microgrid. But if I'm going for the DC microgrid, you can see here the DC network is there. You can say the energy pool as well. And again, these are sources which is already we saw. They are there. It is there. If it is using here the DFIG, the doubly fed induction generator, then it is a AC. And the sum of the loads you can emit from this AC here, and remaining can be converted to the DC KVLN coming here. So it may be your permanent minor synchronous generator. Then you are having completely here the DC, and then you have to basically connect with the DC depending on the voltage. People are talking due to certain problem. Yeah. So the solar irradiance and temperature, that's already you can require the DC to DC is a DC. It is also the fuel cells is DC, battery is also DC. Here, if you're having AC and DC, that's all you can say. Suppose it's a DC, then you require inverter to connect the grid and three-phase loads. But it is a DC, you can say it is directly with the, again, DC converters are required to match the voltage. So here with the 750 volts was required because this voltage decision is very, very important. If you are using very high voltage, then the cost will go high and then converter cost will be also high. If you are using low, the losses will be more and the cost of this will be less. But we have to see what will be the optimal site. So a lot of people have done the voltage analysis also, that's for operation. So you can say all the renewable energy sources are integrated in the DC microgrid. So the advantage of the DC microgrid over the AC microgrid, that the DC microgrid is preferred over the AC EMG because of their several advantages, such as high quality power supply that you can have the DC. That's very well, we can smoothen that and we can supply the DC because you can rectify AC and finally give the DC. And the better reliability and the uninterrupted power supply can be done by the DC microgrid compared to the AC. Better utilization and reduced total loss due to the absence of reactive power. As already I was saying, that's because the DC, we are having a lot of DC loads, and that's the reduced loss that you can do because reactive power is not there. So only active power is there. So the current in all the devices, it's only active current, and active current I square R is there. Otherwise, active and reactive currents should be also this highest used for the losses as well. So that's why you can have the higher efficiency in the DC. Easier control of the DG units connected to the DC microgrid, only the DC voltage control is there. Because it is only that you have the DC voltage you can control very easily and no synchronization required for the multiple DCs because the DC directly they can connect because the voltage only they are matching, no frequency required here that is there. They are having less corona and ischemic effect. Although if you are talking about the microgrid, corona is not a concern because corona doesn't come at the lower voltage and here, but the ischemic effect will be there. So the losses and other things will be there as you know in the AC system. So challenges in the DC microgrid is controlling the DC voltage. A control strategy of the bi-directional three-phase voltage source converter for the integrating here, as well as the establishing a constant DC voltage is required. So already some work we have designed and that's reported in the PS general meeting. It was presented in 12, and that is basically how to decide the voltage, etc. That's a control this voltage philosophy. So it was said, and we found that we can control the wind turbine generator for the controlling the voltage. And once it is maintaining the voltage and all the power we are taking for the wind turbine, remaining are basically used to supplement the power variation, etc. That is basically there. And here it requires more space and maintain the ESS because we recover now the battery. And battery also require this space. And then battery operation, it's also charging and discharging efficiency with the different. They are also having some lossy component, but
Sir, I think so. There is some audio problem.
My voice is low.
Okay. Now it's coming, sir.
It's coming. Okay.
Yes, sir.
So can you see my slide?
Yes, sir. That is coming. Good.
Okay. So synchronization of the DC to utility grid. Now, if you are having DC, then AC, then synchronization you require, because you have to now your converter inverter is there where this voltage and frequency must be matched with the grid control. So that synchronization is there. So only one synchronization if utility grid is there. Otherwise, it's very easy. That's no synchronization. Only you can connect the voltage. You can raise the voltage and connect. So no frequency, nothing is required here. So that is one of the things. So the control philosophy for integration of utility grid as well as the three-phase loads to the DC microgrid are required under the various operating conditions. Another concern is the protection issue, because in the DC, the protection is a big challenge. Nowadays, because circuit breakers are normally based on the AC, because the small circuit breakers which we know. Fuses are, of course, they work in the both AC and DC, but if you are having the circuit breaker that is a control with the, then what we do, if the current 0 is going, that time we chop it so that we can have the minimum flashover and other things due to the voltage gradient. So the protection issue is the concern. So what we do, we are using converter itself for the controlling it for the protection issue, and that is one of the challenge here. So the feature of the proposed DC microgrid, what I'm going to show you, it is the DC microgrid where we are having the architecture. Already I said where you see a DC, but I have taken DC. To facilitate the connection of the any DG energy resources and the various loads. The proposed DC microgrid is able to supply both AC and DC power to the load simultaneously here. Each DG unit has been controlled autonomously without the communicating to each other. You see, there's no communication required. And one is controlling voltage, other are controlling based on measuring the power and other things. So autonomously control strategy eliminates the circulating current among the DGs, because suppose what happens if you are generating from one, another is going to take some, there is a possibility of the circulating current, and that is again, it is a dangerous. We don't want the circulating current as well. It eliminates the, I should I can reduce my board. Give me time so that I can, yeah. So this eliminates the need of the transformers on the load side converter by selecting proper DC energy voltage. If you are having the proper voltage, then we can, basically we have taken 750. So sometimes we require the transformer from the load side directly. We can have, that's the one converter from the AC or DC side, that is possible, which already I showed you here. You can see in DC, we require here, there is no here, you can say DC to DC converter are there only to match the voltage. Here you can say if you are having voltage less, you require another one. Here you can say it is again, we are having the voltage, lower voltage here. Here is we are having one inverter, and very easily that is converting here. So this all together, it depends upon the voltage already I said that is required. So what we have taken, I'll show some of the study what we have done. So the features of the proposed DC microgrid which we have taken, when the wind turbine is 0 or less than the 3-phase power load in the local area of the wind turbine generator, this load is supplied by the other through the bi-directional switch. So what I want to say here, in this, suppose there is this wind is 0. So what happens, this load, local load, that can be made from here, and that is, you can say the bi-directional switch is there here. So bi-directional 3-phase voltage source converter, we are having the AC to DC. So the power will be coming here through this. So here you can say the arrow is double, and the battery as well, you know, the charging and discharging there. But these devices, you know, they are basically, there's no load. So there's unidirectional control is there. Here you can say unidirectional is there, but here is a bi-directional power flow is required. So the control will be in such a way that that will take care of that in that fashion. So the solid state fuel cells is used for power generation, and the variation it basically utilized with the varying loads, and is also depends upon the what is the output of the wind turbines and the DG of the solar power. So if these all balance especially will be met by the fuel cells as well as the energy sources. It is a very, very important whether your energy batteries or storage system is having energy, or it has to be charged, or it will be discharged. So that's the coordination with the fuel cells and the battery is very, very important, because we want to trap complete power of the DG, we want to complete power of wind turbine, and we want to meet complete load. So the variation with the control philosophy that we have with the fuel cells as well as the battery, so that we can control our load balancing and also the voltage stabilize in the islanded mode that we can do. So these are the very, very important control philosophy that we require. So the voltage source converter for the DC microgrid we have used. There is a pulse width modulated based voltage source converter with IGBT switches are widely used, and there are various applications. They are used for the voltage control, power flow control, system balancing, fault protection, maximum power tracking point of the various DGs, and high quality power conversion system, maybe DC AC, AC DC, and DC to DC they are used. So this pulse width modulated voltage source converter is used for completely no current source converter at all that it is used here. So you can say the proposed control strategy for bi-directional voltage source is wind turbine. So this is, you can say it is a wind turbine. Here that the power is coming. This is a voltage source converter. You can say from here AC to DC it is converting, and this whole control philosophy we are doing based on it is that is used. And here is a special integration and the similar model that we have done. It is basically we are converting, you can say, the alpha ABC to alpha beta component, and then from alpha beta is a DQ component, and then it's a control philosophy used so that we can get the gate pulses to the pulse width modulation converter. So the proposed control is in the voltage source for the wind turbine. The objective is to control the strategy is to establish the constant DC voltage of the DC. So this wind turbine is maintaining the voltage of the grid, the DC. And the various operating conditions, it may be normal, it may be faulty. So this control is the first primary is only to control the whatever the power is there, it has to take, but it has to be controlled in such a way that complete power is to be taken. At the same time, the voltage should manage the voltage of the DC microgrid. And it maintains the power from the three-phase load in the local area because already there is something there. Otherwise, hello?
Sir, sorry, actually slides are not moving, I think.
Not moving?
Yeah,
but it is visible. Yeah, 1 minute.
A slide here it is visible challenges in DC microgrid.
Okay. Can you see the slide?
Yeah. Now slides are coming.
So it is a proposed control strategy of the bi-directional. It is visible.
Yes. Now it is visible.
Yeah, because this Microsoft team is not very good. Remember, normally Zoom and the Google Meet is a very fast and problem. Here, yeah, it creates a lot of problem. I know. So whenever you face the problem, just you let me know. Okay. So it maintains the power from the three-phase load in the local area. And when the power generated by wind turbine is 0, then already said the local load must be met, and that's operating conditions must be that various scenarios is generated. The various cases we did, and I'll be showing how it is going to match it. And also we should have the very good power quality conversion system. So that is the three basic objective of the controlling. This is a wind turbine to the DC microgrid. The proposed control strategy implemented in the two rotating DQ reference frames. And the one is a positive, one is a negative synchronous phase reference, and that control philosophy is unique that we have developed, and based on that we are controlling so that we can have a very good philosophy for controlling and the good power quality that can be generated with this one. So the controllers of the DC to DC boost converters for PB and the fuel cells have been also proposed here in this paper. So you can see here it is for integrating the general. I think this slide already I showed to you. Oh, sorry. It's going back. Right, sorry. Yeah. So you can see here this what we use for our system. So we use the wind turbine. Its maximum capacity is 600 kilowatt, and it is at the 690 volt. Why can 690? Because many output of the which is taken from the literature from Germany wind turbines. That is this rating was wind turbine. One wind turbine was taken. The SPV, the photovoltaic, the DG system was having 100 kilowatt. And it was taken at this voltage because it was again taken from manufacturers and the same voltage we are using. This fuel cells, it was 100 kilowatt and its peak capacity is 180. It can go up to really certain chains, it can be go 180 kilowatt. We are having the transformer because we require the transformation from this here wind turbine to this. Your load is 415 volt for the load, local load. It is that it is used. And the bi-directional three-phase voltage source converter rating is more than what the power is there because you have 25% extra. Otherwise, the transformer will maybe creating problem. The load side, you can say the various loads we have taken. It's a 100 kilowatt three-phase load, 100 kilowatt the three-phase voltage source inverter operating here, 200 kilowatt load across the single phase. So the various whatever I saying, so these are the loads that we are in the total load here is a 600. But these are the, you can say, even the wind turbine is giving all the time 600 is sufficient, but it is not so, because this is also varying. So based on that, we have to see the using my control philosophy, which we have developed, which is not here I'm talking because it will be very high level. So only this I can say the various case studies what we did. You can see it is a simulation result of the proposed here. So the variation of generation and the load constant here, the 700 kilowatt. Without here, there's no battery energy storage, and the generation is varying. So you can say this is a wind turbine output is changing, and now it was also said that your solar is also changing like this. You can take any parameters that it was taken, and now if this is changing and my load is constant, so the remaining power has to come from battery since it is not there, so it is from the fuel cells. So it is, you can say, very less, it is trying to meet that power, but and our grid voltage, 750 DC voltage, you can say it is maintained continuously with our control philosophy. So in the case 2, here the constant power generation by wind and air, they are giving the constant power, but your load is varying, but there is no BSS. There's no battery energy sources. So you can say my total load is changing. So in that case, even this total power is, I know the wind turbine and they are constant something generating, it was taken, and due to that they're generating it to their rating, and you can say with this variation, again the fuel cells is trying to match exactly what is there, and the voltage is also maintained. So the power generation by wind turbine is 600, and also 100 it was taken. So 700 is basically taken as a generation, and you can say my load is changing from 800 and it is a 700 to 800 variation. If it is changing, so the remaining power has to come from, you can say here it is a 700, 800 there, so you can say 100 kilowatt, 100 watt, 100 kilowatt, the load will be required. So that you can say similarly it is a matching. So SOP generation varies according to the varying load, and you can say it's a total demand to fulfill the power mismatch up to the limit of the PPC of the here solar fuel cells while maintaining the constant DC rate. My slide is changing.
Sir, there is some problem in the moving of the slide.
Yeah,
now it is started. Now it is started.
No, I know what happens. Okay, I'm just again sharing. Wait. I hope you can see it.
Yes, sir. Yeah. Now it's coming. Fine.
Okay. So it is now the third case we take, everything is varying. Load is varying, generation is varying, and now we are having the BSS. If it is not having, then there is a certain time that your load generation balance is not there. That time the system will be failed. So we are having the battery as well, and in all the battery, it is assumed that initially it was charged, so the remaining power has to come from the battery. The battery is what it will do. If the excess power is there, it will be charging, and if the short is, it will be discharging at the normal phenomena. So you can say this is a wind turbine, this is a solar power output which we have taken, and this is the fuel cells. It is basically it is taking, and these are basically coordinated in such a way that there is a possibility when the battery is not there, then the solar will be fuel cells will be emitting, otherwise it will be zero output. So the battery will be the charging. So you can say the green power is, you can say basically our load is less. So based on that it is changing. So the green power, the battery is operating. So what is happening? The fuel cells and this are coordinated in such a way that my load generation balance will be there, and at the same time the voltage can be maintained up to that extent. And that is one of the concern which we are taking care. So the variable power generations and the load, we can say the voltage here is a constant, and that is the grid voltage. So I already said I'm maintaining the voltage and also the power balance. These are the two controllers that is required in the DC microgrid. So beyond the generation capacity of the fuel cells, the power mismatch between the total generation and load will be fulfilled by the battery energy storage. The DC voltage, you can say, is maintained constant. The intermittent characteristic of wind speed, the solar radiance, temperature has been considered in this whole operation of all the three cases. The variation of the load is also according to residential load demand curve, which was taken already presented here in that this book, this one tutorial, this book, and assume the load is constant for next 2 hours. What we have done, because the load is also changing continuously, it is possible. the controller, then you require a sensor, and based on that you have to do. So the 2 watts we are assuming the load is a constant. If it is not there, then we have to measure take the voltage, all the variations, so that every time you can control, maybe every 5 minutes or 1 second, that we can do. Another approach here, the Y battery. Because battery is another one. Now government is always trying to go for the hydrogen, because it's easy that we can have the hydrogen energy that we can carry, not on the transmission system, we can put anywhere in the various locations. So if you are having more generations like wind and you are near to the sea, we can generate the hydrogen power, and from hydrogen that you can again use, basically that is a convert to the electricity using the fuel cells here. So the storage system which are having the battery and the hydrogen were together, and using this basically again we have used. So an extra here storage system was used, and same control philosophy was used to show all these things. So the proposed control is strategy for the hydrogen energy storage system, that when it will be generating, when it will be utilizing, all the things, a big philosophy is written depending upon the battery energy requirement. So you are having the battery energy, whether it has to, battery has to charge or discharge, or it may be your hydrogen energy. So these two are basically based on that one, that is it is a required, and you can say the duty cycle of the hydrogen energy storage system is basically used. So it is a coordination is required, because when it is a charging and discharging, because my intention is to maintain the power balance and have to minimum cost criteria, and you have to utilize more and more renewable energy sources. So using that philosophy, this control philosophy is developed. The purpose of proposed control philosophy, as I said, to control the charging and discharging of the battery up to its full capacity, and thereafter restore the generated surplus power to the hydrogen. So if let's suppose that even though generation is more, battery is full, then what you are going to do? No waste. You can generate your hydrogen and then you can store. And sometimes these hydrogen energy can be again converted back in terms of fuel cells, and that can be used for the generation. And we have to balance the power all the time here. So again, for this case also, we have done the various cases. It is, you can say, the variable generation of the both VT and your solar power, and the variable loads are there. Then in that category, and the loads are also varying, and your generation, everything is varying. So you can say DC load variation is there. You can say telecom load is variation. Your power generation by, you can say VT, either, and the PV cells are changing. Then what we are going to do about here is, you can say the fuel cells. Here the battery, if it is not there, then what we are going to do. So in that you can say it is meeting here the fuel cells as well. But if you are using the HEC here, then whole scenario just we have to see that's the total power mismatch. If it is there, that can be gone for the battery voltage and battery output power. You can say how it is utilized. So if the battery is charged fully, as I said, it is having complete energy, you can say 0 here, then at that case here the discharging. But there is a possibility that it's having more energy generated by this, then we have to have the discharging as well. So you can say hydrogen energy here, though we have used electrolyzer on voltage because it is converting. So you can say the power to hydrogen energy, you can say it is that is coming here. So this energy is going to the hydrogen energy storage, and then we are using the electrolyzers for controlling the voltage and current, and you can say how much hydrogen is generated. You can say based on that it is hydrogen energy is generated. And you can see by the voltage, the telecom load voltage is constant, the voltage of the AC load is also, and then my DC voltage is also certain. Only you can say there is some ripples at changes here in the various hydrogen energy there, that will be there all the time, as you know, it will be there in the system. Also, we try to see the performance of all these things with having certain fault in the system, because the fault is also there. Suppose there is some fault with the resistance, with the DC fault I'm taking with a certain resistance, and it was found that's a time 1.2 to 0.2 seconds duration it was used, and you can say how it is the fault power is, you can say it is varying, the fault current is increasing. And then you can say the DC voltage, it was continuously the 750, then our controller is working, and in that one it's a controller voltage is going to low, but controller is trying to increase it, and finally you can say it is settling at the same voltage. But there is some disturbance here, and also it is a stabilizing, it is basically coming back to its original voltage, and that is the need of that. And you can say the various load, what is happening due to this fault, you can say the load voltage here, the single phase load voltage is going to be very low. At that time, power consumption is going to be very, very low during the fault conditions. So it is a bearing the load variations are there, but when the fault is going to occur here, you can say there is some problem here. The three-phase load voltage is going to be there. So you can see here in this case also the line to ground fault is done, and now you can say there is a power gap is going to be during the fault condition here. That is the 1.2 second to 1.4 second how it is going to vary. So it is a total, I want to say that is the variation of the output of power of the BSS, how it is the batteries is going to change. You can see it is a charging and discharging. So all this philosophy with the synchronous frame reference controller with the positive and negative is used, and it is efficiently controlling and calculating all the things in this one, and that I wanted to show. So I'll start with the concluding remark that the DC microgrid facilitates the connections of any type of the renewable energy sources, energy storage system, various DC and AC loads, that is a three-phase or single-phase loads, by using the pulse width modulated power electronics converter, and we are using the voltage source converters as well. So the DC microgrid is able to supply both AC DC power to the load with the high power quality. Already we see that the juts are very small. And this is the DC microgrid can operate in both islanded and the grid connected mode as well. And it offers a lot of opportunity in the electrification of the remote area. So the DC microgrid with the suitable control strategy operates satisfactorily under the various operating conditions, even the change in the fault, normal condition as well. And it is giving, there's a small transients are coming during the faults that is always there because any system is there. So it has a certain charging inductances and other things they will be playing and your control, but it is very fast because we are having the power electronics based converter control. We are minimizing, there is no circulating currents within this suppressed, and that's why the control is very useful and no need of the transformer as it eliminates the load side converter by selecting power voltage of the DC microgrid. So with this, I should stop here, and now I'll say there's people can ask the questions if they are having any, and already I think 12 o'clock time was given.
Yes, sir.
So, yeah. And because I have to rush to hospital also.
Thank you very much, sir. Thank you very much, sir, for your wonderful session. And I hope so participants may have got some idea from this session. Any query from the participant side, please, you can interact with sir. It is a golden moment for you all people. Participants, you raise your hand, we will unmute. If you have any doubt, please you can ask by raising your hand, we will unmute you. I hope so, participants.
Good, no issue. They should try to learn and more, and many sessions are going to come, so they can enjoy all these things.
And so, I will request Dr. Singh sir to provide the slides so that we can provide to our participants.
I'll give. Just yes, I'm going to convert it and I'll give it to you. Right, no issue.
Thank you, sir. Thank you very much.
Thank you very much.
Sir, I would like to invite our respected principal, Dr. Joshi sir, for giving some farewell remarks.
No issue.
Welcome. Thank you.
Thank you, Giri sir. I am really obliged again to give farewell remarks for the SN Singh sir. Respected sir, I have been listening to you for the whole presentation, and I am again enlightened by your words and on the technical issue, which is very much relevant in these days. If I talk about my research journey that has started with this kind of lecture by Professor A.M. Kulkarni.
Yeah.
In those days, I was not thinking to do PhD, but then after listening to him, that idea came into my mind, and I had thought of it and appeared in the interview and so on. It's a long story. But then the point is, sir, that I am sure the participants who are present will get some good idea about what is happening in the area of research in the microgrid. You have very nicely explained the different control strategy, how to control the microgrid in different scenario with different facility like fuel cell, wind turbine, solar generation, and even included the battery energy storage system as well as the hydro generation system. So everything is covered by you and very lucid and in a very depth. I could see that you were trying to cover as much content as possible. That has been really a great aspect of your delivery of this content. So I'm sure that all the participants are at the benefit to listen these kind of lectures at the national level. I appeal all participants to take maximum advantage of it. If I have to say that was the Gnan Ganga, which was possible only because of the online mode of this FDP. So otherwise, maybe if there is an FDP at GC Bharuch, it may not have been possible by SN Singh sir to join personally. But then it's a great opportunity that one starting lecture was delivered by the great professor Dr. SN Singh sir. Sir, thank you very much for sparing your precious time.
Thank you, sir. Thank you. Thank you very much.
That has been really very much, we feel very much privileged. Again, sir, thank you. Sadar Vandan, sir. Thank you, sir.
Thank you. Thank you.
Thank you very much, sir. Thanks for giving your valuable time to us. Thank you very much, sir. Thank you. Okay, Joshi sir, now we will start our second session after the lunch break.
Thank you. So, goodbye and we will join again.
Thank you for joining us, sir. Thank you for giving entire session to us, to participants for Moral Booster. Thank you very much, Dr. Joshi sir. Thank you. We are indebted to you, sir.
No. It is my FDP of my institute. Please don't thank me.
Yes, sir. Thank you.
We are part of one team.
Yes, sir. Yes, sir. Thank you. And now Dr. Rajesh Gupta will take the next session at 12:30, sir. All the participants are requested to join before the session, please. Okay, now we will depart for the lunch. Thank you very much. Thank you. Thank you to all. Participants are requested to join before the session and stay till the last moment of the session. Please keep in mind, we are taking attendance very, very seriously. If you are unable to join due to some reason, please inform me. I will provide the link or I will provide the guidance how to join the session. But my request, humble request to all of you, don't lose the session. Don't miss the session. Sessions are going to be very interactive and we will provide all the materials, PPTs and everything related to this FDP. You will enjoy all the sessions, but my request is only you join the session before starting. You people are joining continuously, going, then again coming, then going, then again coming. I don't know the reason, but there may be the reason of connectivity, but please stay till last moment of the session and join before starting of the session. That is my humble request to all of you. Okay, we will meet at 12:30 again. 1:30. Yes. Actually, sorry, there is one miscommunication from my side. Actually, next session will start at 1:30. This session is ended somewhat earlier, and 12:30 to 1:30 will be the lunch break. We will meet again at 1:30. So please take your good lunch, and then we will meet again at 1:30. Professor Dr. Rajesh Gupta is going to handle that session. You all will enjoy. join before time, please. Thank you very much.
If it is possible, Giri sir.
Yes.
If it is possible, suppose after completion of morning session, if the participant mute themselves and keep themselves continuously logged in for the afternoon session, it would be better, I think. So we do not have to admit them continuously in between, because some
not an issue, sir. Suppose there may be some data problem to anyone.
As far as possible, we are requesting.
Yes.
Otherwise, no problem. We will admit everyone.
And from tomorrow onwards, I will not make anyone attendee. Their mic and camera both will be available to them. And because today the session was inaugural session, that's why I made all participants attendee, because sometimes during the inaugural, yes, our expert has joined us. Now admitting him, don't make him attendee. I think so. Dr. Rajesh Gupta sir has joined us. Professor Gupta sir, unmute yourself, please. Hello. Am I audible to you, sir? Professor Rajesh Gupta sir?
He is actually, you have to, sir has to unmute.
We cannot make unmute from this side, na? Sir has to unmute. Yes.
Good afternoon to everyone.
Good afternoon, sir. Thank you for joining, sir.
Thank you so much. I joined. I think I'm audible, visible also.
Yes, sir. Now, without taking much time, I would like to start the session with the introduction of Professor Gupta sir.
Yes, sure.
Professor Gupta sir, there are almost 140 participants in this FDP from across the states, and still they are joining. Some participants have joined us, and someone will join within 10 minutes, 5 minutes. Now I would like to introduce Professor Gupta sir. Dr. Rajesh Gupta sir is a professor in the Department of Electrical Engineering, Motilal Nehru National Institute of Technology, Allahabad, Prayagraj. He received the bachelor's in electrical engineering from the MMUT. Now, previously it was known as Madan Mohan Malviya Engineering College, Gorakhpur. Now it is MMUT, Madan Mohan Malviya University of Technology, Gorakhpur. And sir received the bachelor in 1993, master degree in control system from the BITS Mesra, Ranchi in 95, and PhD degree in the area of power electronics and control from the IIT Kanpur in 2007. From 95 to 96, sir worked in the IIT Lucknow, that is a very well-reputed college in the middle region of the Uttar Pradesh. And from 1996 to 1999, he worked in the GB Pant Engineering College, Pauri Garhwal. Now it is in Uttarakhand. Thereafter, he joined the Motilal Nehru National Institute of Technology. Dr. Gupta sir is a senior member of IEEE, life member of Solar Energy Society of India, and fellow of Institution of Engineers. His research interests includes power conservation of renewable energy sources, solar PV and wind energy systems, power electronics converters and its control, energy storage, electric vehicles, etc. He guided 12 PhD and 55 master students. He was a principal investigator for the research project sponsored by various ministries, including DST, SERB, CSIR, and MNRE, in the area of solar PV and wind energy systems. Bi-directional converters, hybrid renewable energy storage, and microgrid. He has filed 3 patents. He has filed 3 patents in the area of bi-directional hybrid converters and hybrid power supplies. Dr. Gupta sir has served as a vice chairman and secretary in the IEEE Uttar Pradesh section and IEEE joint chapter of IE, PLS and CES. He is a recipient of 2013 IEEE Outstanding Branch Counselor Award of Region 10 of IEEE. He is also recipient of 2014 IEEE Outstanding Volunteer Award of IEEE Uttar Pradesh section. He was a first prize winner of VI Mantra contest in 2006, organized by National Instruments. 2 of his PhD students and 2 master students have won POSOCO awards sponsored by Power Grid Corporation of India. Being an electrical engineer, we are knowing the POSOCO and its importance. In association with the IIT Delhi, he has traveled many countries under the university exchange programs and attending the conferences including USA, Canada, France, Sweden, China, Poland, Turkey, Thailand, Japan, Singapore, Portugal, etc. His name appeared in the top 2% scientists in the world under the category of electrical and electronics, published by Stanford University consecutively for the year 20 and 21. Dr. Gupta sir is serving as an associate editor of IEEE Transactions on Energy Conversion and IEEE Power and Energy Society Letters. So Dr. Gupta sir's achievement is inspirational. His contribution is phenomenal for the community. And today we are very much privileged to have Dr. Gupta sir with us. And I am very much thankful to Dr. Gupta sir for accepting my invitation for delivering the session in this FDP. And participants definitely going to be enlightened by him. Thank you, Dr. Gupta sir. Thank you very much to join us. Thank you.
Thank you, Dr. Ashutosh, for giving my introduction. I am really thankful to you for giving me opportunity to interact with all of you. I am also thankful to your institute and this Atal organizers, Government of India also, for making me part of this program. So thank you so much. I thank all the participants. I just came to know that there are many participants across the country. So I'm sure everybody is enlightened to attend this short-term program. So it's nice. I'm sure you already had one lecture in the morning, and I think today is the first day. So afternoon is little bit not very comfortable for everyone to lectures, but I would like my level best to keep you awake and try to have your attention. At any point of time, if you have questions, you can always ask. You can interrupt me and ask the question. So now let me start. Let me share my slides. Okay, I think I have shared my slide and I hope it is visible to you all.
Yes, sir. Now slides are visible.
Okay, thank you very much. So title of talk today is DC-AC hybrid microgrid for low power distribution system. And I come to know that, the reason for choosing this topic because your DP is on this topic, microgrid. So I thought, let me choose the topic which is very close to the theme of the FDP program. We have little bit experience on working with the microgrid and hybrid microgrid. Although let me clarify that because whenever we talk about anything in the power system which has a mix with the loads, there is always two aspects of study. One is power system and other is power electronics. And different people give the view of the system in a different way. Power system people will try to give the view of everything from power system point of view. And power electronics people will try to put up the things from component point of view or power electronics point of view. So let me tell you that I am from power electronics background, and I have a good experience in working with the low power distribution system. Earlier worked with the compensation, power electronics compensations. Then we worked a lot in the renewable and distribution systems like solar and wind. And now we are having some experience on microgrid and hybrid AC/DC microgrid. The source of these experiences are that recently we completed a project with Ministry of New and Renewable Energy, MNRE, Wind Energy Section, Chennai, and their head office in Delhi, on the topic AC/DC hybrid microgrid for residential rural application. So through that, we try to develop some of the models which may be useful for residential rural application. We had recently some of the publications in IT, generation, transmission, distribution, GTD, IT power electronics. Then couple of publications we have in IEEE transactions on industrial electronics 2019. And recently we have one accepted publication in the IEEE selected and emerging topics in power electronics by IEEE. So I'm just giving you a brief. If you are interested in these topics from power electronics point of view, so you can go to these publications to have more detail. So I will be listing some of the things which we have done in today's publication, recent things. Before I go to that, let me give you some brief introduction, what is all going on recently. So there are certain recent things which happened. I just collected these points which we have seen and which we have certain data with me. So first of all, as you all know that microgrid and the main grid are supposed to incorporate the renewables, and therefore there are a lot of research scope in these areas, especially if you go to the microgrid, renewables and EV charging, electric vehicles. So these are all the low power applications. So we have a lot of scope of research in these areas. So to start with, first of all, everybody knows that India has an ambitious target of achieving 175 gigawatt of energy from renewable by 2022, right? So 2022 is already going to end by this March. So accordingly, 100 gigawatt through solar, 60 gigawatt from wind, and rest of the 15 gigawatt from bio and some other form of renewable energy. So this is an ambitious target. The country is well set to achieve this target, and it's already achieved almost. Then India has another target of producing energy capacity through non-fossil fuels to 500 gigawatt, right? Including all solar, wind, hydro, non-fossil fuels, right? We don't want to burn the coals. And this will be approximately 50% of its energy requirement by 2030. So this is next target. After 2022 target, the next target is 50% from non-fossil by 2030. So for that, there is a continuous monitoring system through web-based online system, especially solar and wind. Then the government already decided not to add any coal-based capacity between 17 and 22. That's what the target of the government. And it's really not happened. No new coal-based addition took place in this period because of some reasons, like everybody know, that the government has to follow the global target of net zero carbon emission. So that was already, I will be detailing you. But yeah, after 2022, there has been some addition, especially in our region. Allahabad, we have two coal-based thermal power plants. One is major thermal power plant, that is 660 multiplied by 2, and then another is the Tata power plant, 660 multiplied by 3 in our very close area. So we have seen that we got information that NTPC has been sanctioned in our major power plant, another supercritical thermal power plants of about 800 megawatt capacity. So looking into the requirement of energy, government has initiated the permission to go ahead with the new power plants. Central Electricity Authority has revealed that the planning model selects the battery energy storage from year 27-28 onwards, and a battery storage of 2700 megawatt is projected to be the part of installed capacity in 29-30. So another important development is taking place in the storage. So I must say, if I am saying about the microgrid, there are 3-4 things which we must know. One is the renewable. Another one is this EVs which are coming up, right? And the third one is the storage. So these are the very significant things. And storage is also one of the component of this, our smart microgrids or smart grids, which is going to play a major role. And the storage is not going to be limited only to our batteries to be used in cell phones and inverters at our home or laptop, but it is going to play a role in a coming future for microgrid applications and grid scale applications. So there is a new word coined which we call grid scale application. So government has targeted that by 2030, about 27 gigawatt of storage, leading to about 4 hours of backup for 108 gigawatt hour of energy to be the part of national the installed capacity. So that's a major information to everyone that storage is coming in a big way. Recently, we had a climate summit at Glasgow, which we call COP26 meeting, and India has pledged to reduce the carbon emission with a target of net zero carbon by 2070. So this is one of the very important information to, again, I hope everybody know, all of you know it. So in this, achieving this target of net zero carbon emission by 2070, we have to do a lot of exercise. And as a power engineer, it is our duty also. And as a young faculty members, all of you have to teach your student also that the ways and means to achieve net carbon zero emission or the electricity power generation by ultimately by 2670. So in the same meeting, there was another very important development which took place in a way to meet this net zero carbon emission. One sun, one world, one grid. GGI also WOG. That is Green Grid Initiative. One sun, one world, one grid. And the idea is to aim to harness the solar energy, okay, wherever it is there in Earth. Because as we all know that solar energy is something which is available throughout. There is nothing like that sun is not generating its energy. It is only that we are only able to gather this energy in daytime, and in night time we are not able to harness it. But the point is that this energy can be harnessed from any other point of the earth. So if I am sitting in this, at this time in India and I am able to capture the solar energy, Australia may not be having right now, or the US doesn't have the same solar right now. So maybe when we will be having a night time, it will be there. So why not to have a green corridor? Why not to have a mega grid, something like the global grid, and a global interconnected solar power grid, that way we can call, which actually able to transfer the power wherever it is available. So that's the idea, and it is targeted that 2600 gigawatt of interconnection may be possible up to 2050. So that's a huge target. 2600 gigawatt is a huge target. Maybe it is it's a international, but still it's a very big target which may be possible in an initiative to strengthen the country's requirement of green energy. Recently, we all see the coal crisis, and in October, especially post-pandemic, when we saw that there was a lot of activity around, restarted with industry in full-fledged started, and there has been we all heard the news that due to the coal crisis, our grid is under threat. So that was one of the also facts, because and these facts will keep on coming to us. It's not a temporary fact, because moment you go away from the conventional power resource, right, you will be facing and you will be approaching towards the green energy. The reliability aspect will be very important, and then you will be losing, because as much right now we are sitting in a very comfortable position because of the very reliable power generation from our conventional thermal generators or generation units, and we can generate the power 24/7 for throughout the day, throughout the week, throughout the month, throughout the year, if it is required, because it is all controlled resources. Whereas if we talk about the green energy, most of the time they are uncontrolled and they are not within our control. So definitely, if we move from controlled to uncontrolled, we will be losing the reliability of the system. And that was the reason that we faced recent crisis also, although it was a very small crisis which led to the coal reserve of just 1 or 2 days for every thermal power plants. But now the situation has restored, And most of the time, the thermal generators or thermal stations have a coal reserves of about 12 to 15 days. So it's a fact. We should know that how important is our conventional resources, and that fact got unearthed to us when we saw this crisis recently. So these were some of the information. Then, as far as other information is concerned, solar tariff is very low, and it reached to about 199 rupee, 1.99 rupee per unit of the cost, with the introduction of 40 gigawatt of 500 megawatt of our solar projects, especially in your place. I noted down this information. And in the same time, 30 gigawatt of wind solar park was there in the month of December 2020, and I think it is now operational. So these are the part of our targets of 175 gigawatt. And in our place also near Allahabad or Prayagraj, we have a Riva solar power plant. There also we have about 2 rupees or something, 2 rupee 40 paisa of price of solar power per unit. So these are few facts which are actually encouraging every one of us to know that we are going in a right direction of achieving the our green power initiative and net carbon zero emissions. Another very important information as far as this microgrid and this standalone PV power system is concerned, that EVs could account for 43% of total vehicles by 2030. So when you will be seeing about 40% of the vehicles on road, so definitely EVs need a power for powering them. You need some important infrastructure like battery charging stations, and then motor drive systems and all those things. So very soon, I mean, I can say within 6 to 7 years, there will be a lot of changes in our conventional generation, transmission, distribution. So generation, transmission, distribution, which we are very well knowing about, conventionally we are studying power system. Maybe our curricula has to be need to be revised within 4 to 5 years, because the conventional scene of power system may be changed very recently because of these, whatever the facts I just explored with you. So some idea about installed power capacity. This is what current status. By 13th November, we have about 392 gigawatt of installed capacity. Out of that, 59 means 60% is from thermal and 26% from the renewable, 104 gigawatt by renewable. But although we are at 175 gigawatts, so within a month, this data will tremendously change, because most of the units are ready, but it is still not grid synchronized. So we need to wait for it. But you can think of about 30% of power from the renewable by this year. Thermal, as usual, will be about 58% by this March. Breakup of renewable out of 104, which is officially grid connected. Solar is about 48.5, which is close to half, or even more than half after 31st March. But right now we can consider it to be half, 48.5 gigawatt, and then wind 38.4% means 40 gigawatt approx. And others are steady at the same level. We have a very big potential, about 1,000 gigawatt of the potential we have for the renewables in our country. Out of that, 750 gigawatt is for solar. So we well aware about the targets. We have a huge potential of solar. That is why we are going ahead with the solar projects. And we have so much of big targets in our country, like 500 gigawatt from non-fossil fuels. It's a huge target. And it is because of this we have a potential. This, 100 gigawatt is a potential for this March by 2022 from solar, 60 from wind, and 5 gigawatt from hydro, small hydro, and bioenergy about 10 gigawatt. So altogether, this is the targets, and it's already achieved. This target is already achieved. This is some global scenario. This is a global scenario. If you look upon the world, and world actually counts for non-fossil fuel, which is actually renewable, non-fossil or renewable, we say all together. So China is a leading with 758 gigawatt, and this is the data up to 19. Then US is 264, Brazil 141, and India is approx to 128 gigawatt of renewable, and remaining countries. So not bad, India is there, but of course compared to China, we are still about 1/8. So that is really uncomparable. Something has to be done. Government is already doing, but that's the fact about the renewable, and therefore our infrastructure for grid and microgrid. This is a global energy map. You people can look upon these map. It's a very important, and you can type this URL in your Google, and you will see that at any part of the world, at any point of time, maybe 10 years back, what was the situation of renewable, you can see very comfortably. So this is one information. Maybe some of you are looking into it, but it's a useful if you want to know what is the capacity of renewable in a country or in any at any point of time, not only today but for past 25 years. So that's a very good information you can have from this map. Some of the challenges which poses once you have a distributed energy for integration with the grid or microgrid, because at the end all the renewables or all the storage, all these distributed loads like EVs and latest our gadgets which are smart gadgets lead to some or other problems in our regular power grids or microgrid as well. What are these problems? All of you, I'm just going through the keywords, but most of you are well aware of these things. Like power quality is one of the major aspect which for past 20-30 years everybody is studying regarding our very old power quality problem is the reactive power flow and leading to losses, voltage drops, stability, instability, and that is through the that's basically the cause of this harmonic distortions, right? So sag and swells, all of you know, and all these problems are leading, and we need solutions, right? We are working, everybody is working for, especially last 2 decades were dominated by power quality problems when we developed active power filters, custom power devices, fax devices. They all towards the addressing the issue of power quality. Another problem is the reliability of the system. definitely once these so many integrations with this internet is playing a major role. There is a cyber security problems apart from the management of power. So these reliability is also one of the important aspect. Safety and protection, another challenge which we have to look upon very closely once we are keep on developing these resources and loads, because now if you are driving a EV, right, you are like a load of power grid. You are standing somewhere charging your batteries. So you can think of, the safety and protection. The battery should not overcharge. It should not get heated. It should not, because there may be incidents. So load protection. Uh, uh, so all those relay operations and all, solar PVs there. So many things. Load management, it's big thing. Load management has to be done at all levels. At the grid level, we have load dispatch centers. At our state levels, we have a regional load dispatch center. We have fault, right? They cannot take into the account fault. If you all of you are well aware that your solar grid connected solar plant, which is installed in your institute, in your college, is grid tight, and consider the situation when your 50% of the power is from the solar. Then what will happen? Think of the such situation. 50% of the power from the solar, and there is a fault in a grid, national grid. All those 50% will immediately shut down. Now there will be a blackout, the grid failure. So it's a big problem, which we have to look for some solutions for this. And the solutions which are coming is grid scale storage, grid scale battery storage. That's what is coming up very recently. So, and then grid operation economics. Ultimately, economics is what drives everything, right? If you go into the load dispatch center, regional load dispatch center, you will see it is all tariff based. The generation unit, which has a minimum tariff of power generation, will be demanded first. So it is all hierarchy. The supply of the power, which is costliest, will be asked only in the emergency situations. So these are the kind of challenges with us, which we need to study, which we need to take care while we are teaching to our student and while we are doing our research. Other challenges which include, apart from our above important one, like imbalances, load power demand, instantaneous active reactive power control, so many other things, islanding, grid connected mode of operation, islanding mode of operation. Whenever you go for so much of scenario which is changing these days. Now, there is a paradigm shift in the renewable integration, especially if we look upon the microgrid operations. Our classical way of generation of power is you forecast the load and generator fleet has to follow the load, right? So that's what happens. You sit down in the load dispatch center and you see that the load dispatch center gives the targets to generating units half an hour or 24 hours or whatever. So you basically forecast the load, and then generators are given the targets to generate their power or keep ready their power. But the new regime is coming with a distributed generations and with the distributed loads, that you forecast the load as well as the renewable, because now the load is independent. The generation of energy from renewable is also unpredictable. So you have to forecast them. based on the weather condition, based on the data, average data and all. Like we study the big data and all those areas. So this is another area where you can utilize those things. And then you find out the net load. Means you forecast the total load and forecast the renewable energy and subtract them. You will get an information of net load. So net load, that is load minus renewable, and then the conventional generation. The rest of the generation has to follow the net load. So this is the new way of generating power. Along with that, you have to keep ready your storage and distributed generation, and the whole thing has to become a flexible power system. So that's what the scene of our coming generations and our loads and our renewables. Little bit of storage, as we all know that storage is going to play a major role, because storage can act as a generator, they can act as a load also, because as a load you have to store the power, but they can act as a generator because they can meet out your peak demand as well for later use. They are useful because of their good efficiency, especially the electrochemical storage like battery storage have got a very good efficiency. We have to use DC to DC or power electronics converter for management of power. So those are the features of storage, and we can see the intermittency in the solar PV generation. You can see this is a true map of solar generation. You can see how there is a typical variation of solar power in a day, right? Starting from morning to 6:30 morning to 5:30 evening. This may be the scene of solar PV power. So you can see how unreliable and how unpredictable it is. Similarly, if you look upon the wind map, you can see the speed of the wind is changing, and wind power supply will accordingly be changing, because wind power is cubic proportion to the wind speed. So that's another very significant uncertainty over the power supply. Now, if 50% of the power in the system will be like this, then you can think of the kind of reliability of the power and kind of availability. So you have to ultimately forecast these loads, and then you have to keep your storage ready for supply, right? So storage is required for variation in energy demand and load, variation in energy supply, interruption in energy supply, transmission congestion, demand for portable energy, efficiency of energy system, energy recovery. So this is how the energy storage is supposed to play a role for unreliable generations like renewables. You have to keep ready in parallel the storage, so that at the end we supply to the load which is constant. Because if you have a load, it is not going to accept the power like solar. You have to be ready to supply such power to the load, which has a constant in nature. So definitely there is a role of storage, and there is role of renewables along with the power electronics, which is supposed to play a major role. Another important keyword, let me put in front of you, is a grid scale storage. Now, this is a word I mentioned that by 2030, about 2500 gigawatt hour of the storage will be there in a system. And it may be including the battery storage of the vehicles also. So the two very important storage, like the grid scale storage, which is actually the lithium ion battery, and the pumped hydro storage, which will be going to play a major role in a future power generation. So considerable increase in the stationary storage, also called battery based storage, tends to increase for the grid utility application. So battery storage is very, very important, And it is so important that not only it is playing a major role in our domestic loads, like everyday life is dependent upon the battery, like your mobile phones. You are traveling with a storage. I'm talking to you through a storage using laptop. My house power is lightened up with the inverter, which is having a storage. So you can understand the importance of storage at our home. But now this storage is also going to play an important role at the grid scale. So no more a storage a low power unit. It is going to be a high power unit. As I just mentioned, by 2030, the PV plus storage is somewhere between 110 gigawatt hour to 160 gigawatt hour, right? So that's the 28 gigawatt I mentioned, and for 4 hours backup, it will become 110 gigawatt hour. So 28 gigawatt is what projected by 2030 for the storage, right? And that will be supposed to produce 4 hour backup, and it is all required to meet out the intermittency in the renewables. We have certain our national status also. It's not like that storage is just like a concept. Although it has been adopted in most of the countries like Australia, Singapore, and many important countries, but it is also coming in our country. 108 gigawatt hour by the fiscal year 29-30, as per the Central Electricity Authority, just I mentioned, right? And India's first grid-scale battery storage is there in Delhi, installed in February 19 by Tata Power Delhi Distribution Limited. A pilot project of about 200 kilowatt hour storage. Lithium-ion battery storage is used in normal battery energy storage, and it will serve the multiple applications and could pave the way for adoption of smarter energy network based on renewable across their country. Recently, NTPC has also started the procurement of 1,000 megawatt of the battery storage for their various units. You can see the role of, now you can see very well the generation. There is a conventional generation. There is our load bus, like 150 kV load bus, 150 kV bus, 20 kV bus. So you can see the importance of storage and renewable throughout this distribution system. So something like this, we have a microgrid, which could be a small microgrid, where we have renewable energy storage. We call it as MVDC or HVDC, high voltage DC transmission bus, and then it could be transferred to main grid. And you can see the importance of storage for generation leveling, congestion relief, frequency regulation at generating station, frequency regulation, load leveling, you can see here. Then voltage regulation, power quality, all these are required at different distribution levels, right? So now typically, if we come to the microgrid, I'm just giving you the background, all these background, because microgrid is something which is at a distribution level most of the time, at a low voltage level. So all these issues which I just taken up are most of the time in the low voltage distribution level aspects. So microgrid is a low voltage distribution system with distributed energy sources such as micro turbines, fuel cell, PV, wind, etc. Storage like flywheels, energy capacitors, batteries, and controllable loads. Right. So it mainly consists of three things: your resources like solar PV, your storage like batteries, and the loads like EVs, right? So if you just take a single thing, solar, battery, EV, it could be a part of a microgrid. But in general, you can have many things. These systems are interconnected to the medium MVDC, but may also be operated isolated from the grid in case of fault in the upstream network. So that's what the microgrid is, right? Decision making and control is distributed in a microgrid. Power flow is bidirectional. Unlike the main grid, the power flow in a microgrid could be a bidirectional in nature. This is how the microgrid can be represented. You have a mega grid, and this is a microgrid. You have a storage, you have a flexible DG, right? They can combine from redundancy to asset intelligence. Redundancy in assets to intelligence. That's what the paradigm shift is, what we are going to do. Right now, we have excess of assets. We have created a lot of assets for the power in a transmission, generation, and distribution. Right? There are a lot of generation which are keep idle. You know, they are there to ready. We are paying salary to the employees, but they are not generating power. So it's an asset we have created, and we have made it like to have a redundant system. If anything fails, then we have a backup plans and all those things. So this is an older concept. The newer concept is to have intelligence. We have a limited resources. We want to utilize it optimally. So intelligence is required, right? So demand response and smart network technology, what interfaces with the microgrid and a mega grid. This is what the way we go for. This is the power grid. This is the microgrid. You can see microgrid controller, point of common coupling, a conventional power grid. Then it is connected to the microgrid through a point of common coupling. The microgrid controller is synchronized with the main grid. And then there are two-way communications through sensors and actuator to transfer the main power in the loads and in a generation. So both the loads and generations are there in a microgrid along with this storage. And this is how it is controlled in the standalone mode. This link is bricked and you can work isolated. But in a grid connected mode, you have to interface through synchronization with the main grid. So features: remote area electrification through renewables, deferment of investment in bulk transmission and distribution network. So instead of making a huge investment in transmission and distribution, it may be useful to invest in a microgrid. It can improve the energy efficiency, right? It can reduce energy losses in a network. Long light losses, we are worried for a long time. It can be reduced, right? If we have a generation and consumption both at the same site. It can support the main grid as a controllable load and as a controllable generation. It improves the reliability. As a single unit, solar may not be reliable, but as a microgrid, it could be reliable for a main grid, right? Saves from mass outage or blackout. So this is all the future will say that how it may work. There are certain architectures of microgrid, distributed energy resources, energy storage, AC/DC loads, interlinking, interfacing converters. So these are the components of a microgrid. Resources like solar, wind, fuel cells. These are the resources as a generations in a microgrid. Energy storage like lithium-ion batteries or lead-acid battery at a small level, lithium-ion battery at the grid level. Then DC-AC load, you can have both AC and DC loads. in a microgrid. Then interfacing of all these through, if you want to make an interface with a grid, interfacing converter, interlinking converter, so AC DC, DC AC converters and all DC DC converters required. Microgrids are classified into AC microgrid, DC microgrid, and hybrid AC DC microgrid, depending upon the way AC and DC buses and corresponding system elements are connected. How they are connected? If it is purely AC, it is AC microgrid. DC buses are there, DC microgrid, both AC and DC, it's a hybrid microgrid. You can see this typical figure. Microgrid could be connected to the main grid through power electronics interface, like then it is connected to the grid scale storage through DC-DC converters. It is connected to the AC load through inverters. It is connected to the DC load through AC-DC or DC-DC converters. Then it is converted to the wind, solar, microturbine, fuel cell through DC-DC or DC-AC or AC-AC or MPPT and power transfer, respectively. Depends upon what ways you are doing. And then you have a microgrid which is interfaced to so many of these equipments and the systems. This is a typical ESS application at microgrid, smart microgrid, which we little bit started in our lab some years back. So took a typical DFIG and then SCIG. This is a DFIG, double-fed induction generator. This is SCIG, squirrel cage induction generator. We have a solar. You can see the solar PV plant, and then this is PMSG. So typically these are the main resource in a distributed generation, especially in the country like us. Wind turbines with like DFIG, very popular. SCIG, squirrel cage induction generator. Both of them are directly connected to the grid. DFIG is connected through rotor to the grid with a back-to-back converter, and SCIG is directly connected to the grid. Both of them has their advantage and disadvantage. But as far as synchronous generator is concerned, we have a permanent magnet synchronous generator which is connected to the grid through fully rated converters. So this is partially rated converters and this is fully rated converters. Solar PV is connected to the grid through two-stage or single-stage conversion. For more precise application, we have MPPT converter, DC-DC, and then inverter DC-AC for grid connection. These are the industrial loads, residential loads, commercial load. So load is a part of a microgrid. Then this is the main grid, you can see, and this is the storage, like battery storage, and we have a bi-directional DC-DC converter, and this is what we have, this storage. We have worked a lot in this DAB, dual active bridge converter. We have filed few patents on this aspect, especially the high power storage applications and the bidirectional power flow. These are the various structure of microgrid, like AC microgrid, totally AC microgrid. You have AC supply through a point of common coupling. You connect, run your circuit, and then on this AC bus, this is a AC bus, you have AC to DC converter, to DC to AC converter, two interface PV, capacitor, ultra capacitor if you have, it could be through DC AC. Then wind turbine, you have a two-stage conversion, AC DC and DC AC. And similarly, you have battery, then you have DC to AC again, then you have a loads, AC loads. So typically, this is the structure of AC microgrid. A DC microgrid, you can see here, your main grid has to be first converted into the DC. So AC to DC converter, and then DC to DC, DC to DC, AC to DC for wind turbine, and then DC load. And if you have a AC load, then AC to DC converter. So these are the two typical structure and very understandable structure of a microgrid. This is a hybrid structure, hybrid microgrid. This is a typical AC feeder, and this is typical DC feeder. The DC feeder has first AC to DC converter, and then you have all those things which we have discussed earlier. AC loads are connected to AC feeder, and DC loads are connected to the DC feeder. AC microgrid configurations, as discussed, consist of already discussed. You can have a 3-phase, you can have a single phase. Both the options are there. And then other challenges like coordination control, the converters control, the distributed generation transfer, integration of AC. All these are the important aspects in AC microgrid. And the other research areas are like voltage sag and swell in each phase, grid voltage imbalance conditions, reactive power requirement, active power curtailment. These are the challenges in an AC microgrid. This is what one structure, we were doing in our lab. So for the AC microgrid. This is a typical decentralized AC microgrid structure where you have like solar PV installed at every house, and then it's a very popular, I would say. But yeah, the control is also there on a distributed way. It is controlled. So your house is generation, your house is load also, and your house is control also. So everything is there, and everything is connected to the main grid. So this is how the 3-phase supply is distributed through single phasing to each of the distributed loads. So decentralized distributed energy generation. So hybrid AC-DC microgrid configurations are like coupled AC hybrid microgrid. That is, the AC network of microgrid is directly connected to the grid by a transformer, and a bidirectional AC to DC converter is used for the DC network. Right, this is coupled hybrid AC microgrid. Decoupled AC configuration, it consists of bidirectional AC-DC and DC-AC, which means there is no direct connection between power grid and AC network of microgrid. So this is coupled, you can see, completely isolated. This is partially coupled, and then this is decoupled. We have multiple stages of converter. So through main grid, these AC DC microgrid are decoupled, right? So this is for the structures. So 2-stage completely isolated, 2-stage partially isolated, 3-stage partially isolated. Okay, control of microgrid consists of 3 levels. It's hierarchical control, primary control, secondary control, and tertiary control. So primary control sets inner current control and voltage control levels to halt the deviation in grid frequency and voltage amplitude. Then secondary control acts as a centralized automatic generation controller and checks steady state error in microgrid, voltage frequency using communication system. And tertiary control responsible for optimize economical constraints, microgrid operation, and setting in interaction with the distributed network. So first is the primary control, which is actually the power electronics control kind of thing, totally power electronics control. The second, and these are generally the voltage control loops or current control loops, local voltage or current control loop, which are actually controlled at an instantaneous level, right? And the secondary control is the next level of control, which is mainly responsible for generation of references for primary control. And the third level of control is totally economical control. We'll see that you can see here primary control, protection schemes, power sharing, voltage frequency stability, current and voltage controls. This is the primary control. Secondary control, droop control, active and reactive power control, grid synchronization. And the tertiary control, market participation, interconnection, coordination of multiple microgrids, optimization of variables, cost efficiency, etc. So it's totally a hierarchical control. That's what mentioned here, and you can see again the same thing. That's very more illustrative from the point of view. You can see the primary control here. How we control our converters, it's actually the primary control. You can see here. So you use the sensors, you use the actuators, and then you generate the references for current and voltage based on real and reactive power. Then you can see the secondary control. You take a PLL, phase lock loop, like DC link voltage control or grid voltage control, and this is how you control this primary level, secondary level. And then the tertiary level, you get a references or the market scenario, or you get a information from the load dispatch center, and then your control will be actuated. So this is how you go for a control of these microgrid, 3 levels, which we call hierarchical control. Control of power converters in microgrid. We have 3 modes of operation, like grid forming mode. We call it islanded power converters, right? System voltage and frequency is regulated by balancing the generated power and load demands when the microgrid operates in the islanded mode, right? Then grid feeding or grid connected power converters. Units adjust the output active and reactive power, P and Q, based on the power dispatch strategies or frequency and voltage variation of the load or feeder while operating in grid connected mode. So grid connection is always challenging because there is a requirement of synchronization with the grid through phase lock loop. So you have to follow the grid frequency and grid voltage variations. So that's the grid connected mode. And then grid supporting means when you have ancillary services, you need to supply from these converters the reactive power, the harmonic power, or to extract the maximum power from the solar PV or something like that. So this is the way you can use your converters in a microgrid. So microgrid is actually not only the power electronics, but it is actually the combination of power, intelligence, and IT and communication to make it a microgrid, a smart microgrid, right? So smart grid is an amalgamation of electrical infrastructure, information, and communication technology. Right. So collection of real data. This is how we do it. Collection of real data from sensors across the grid. High speed, sufficient and efficient communication. Intelligent computation and IT infrastructure. Real-time analysis and control. So this is how collector to displayer or assessor to resource to controller, and they go like this to have the complete smarter microgrid. Something about this. Now I will be little bit specific to what we are doing in our group or our lab. Some of the examples we have done through some of the experimentation, lab implementation, and other things. So this was the work initially we did with the solar PV system interface to the single phase AC grid. That's what the initial work we did. So we took the solar PV along with MPPT through DC-DC converter, and then we created a 340 volt of LVDC, sorry, MVDC, 340 volt like DC microgrid, where you can connect the DC loads, and on the same DC grid, we connected a bidirectional DC-DC converter, and through the grid storage, battery storage, we can control through Droop control or through the primary control all the converters and the voltage across this microgrid. Now, as far as AC load is concerned, we have an inverter across this DC grid. Then it is connected to the AC main grid and bidirectional DC to AC converter. For single phase, we use edge bridge, and then we use these primary control, voltage and current control by taking the voltage reference and current reference for AC single phase grid. So loads are there, AC loads. So you can see this is a small work we did in our lab. This is the DC microgrid, and then this is the AC microgrid. I mean AC grid, you can say, conventional AC grid, single phase AC grid, but actually it is a DC microgrid. So we just try to implement a small DC microgrid with conventional single phase available in the lab, right? This is another work we did. This was exactly one of the project from MNRE, Ministry of New and Renewable Energy. It was done in about 5 years back. We got a project. So hybrid AC-DC microgrid. We tried actually the solar and wind. So both the resources we actually interfaced on a 380 volt MVDC. That's a standard 380 volt MVDC. So what we did actually, we had a solar PV installed in the lab, about 2 kilowatt, and then we procured a wind turbine emulator because I mean, unlike your place in Gujarat, in Uttar Pradesh, the wind potential is very poor. The average wind speed is about 3.5 meter per second, which is insufficient, which is well below the cutting speed. So we actually procured a wind emulator of about 1.5 kilowatt. And then we try to combine them through 380 volt DC bus. Now it is interfaced to bidirectional converter, which is capable of transferring DC power to the AC power, single phase AC power. And also it is capable to transfer from high voltage DC bus to low voltage DC bus, which we call LVDC. So this is MVDC and this is LVDC and this is single phase AC. So, and then on the small scale, on the small voltage like 24 volt DC bus, we had a battery which is interfaced through a bidirectional DC-DC converter. We have supercapacitor, which is again interfaced through a bidirectional DC-DC converter. And this is DC-DC buck converter for low power DC loads. So this is all we implemented in a laboratory for operation of hybrid microgrid like MVDC 380 volt bus for synchronization, AC loads like our conventional AC load, like these loads, TV, fridge, AC, right? Our bulbs, LED lights, television, etc. That is a typical AC load. Now the idea is that can we have a small DC loads also, like your DC fan, we have a DC charger, direct DC charger. So for that you can have a DC bus, right? So DC power generation, AC power generation, and then this two different types of wind and solar. So this is a totally good work, one of the work we have done. And then we had energy management. We generated the references and controllers implemented. So this is exactly, this was the idea, and then we implemented like this in a lab. So this is PMSG wind turbine through first of all rectifier and then boost converter, and then interface to DC bus. Then solar we connected through boost DC-DC converter for MPPT and control. Then we have a battery which is connected to the grid through a bi-directional buck boost converter. And then we have a supercapacitor which is also connected through a buck boost converter at a 380 volt DC bus. And this is all managed or controlled through a droop controller, microgrid droop controller. Then we implemented edge bridge through IPM, Intelligent Power Module, to feed the AC load. And then if we need a DC, small DC load like 5 volt DC load, then we have another buck converter which is capable of converting high voltage to the low voltage. And if you have a MVDC directly, so this is a 48 volt bus through a buck converter, and this is directly a 380 volt bus for MVDC loads. So this is all the scenario we tried to implement. These are the data which we used, and about 1.5 kilowatt residential kind of system we used. These are the results we obtained. I mean, based on the various scenarios, like solar PV is there, its radiation is changing, then LVDC load is on, MVDC load is on, wind turbine speed is changing, you can see. So all these things will be in such a way that AC real and reactive power is maintained constant, irrespective of various changes and various demand change. So that's what, and these are the instantaneous figures which says that how the current is tracking, how the DC voltage is controlled, right? So all these things are depicted here. Both LVDC and MVDC buses are controlled. Then in a grid connected mode, which is passive, this so here you can see the performance of the battery storage also has been shown, and then power feeding to the grid, then power fetching from the grid in the both scenario when the solar is there or when the solar is not there. So, or when the solar is sufficient to supply the load as well as it has excess power, so it can be, the power can be fed to the grid. And if solar is insufficient, then power can be fetched from the grid. So it is all mentioned in this particular block. And here we have shown the battery responses, the state of charge of the battery charging and discharging. Islanded mode, standalone mode, we operated the system in voltage control mode. In grid connected mode, we operated the system in current control mode because the power balance has to be maintained. In islanded mode, it is important to maintain the constant voltage because grid is not there. So voltage need to be maintained constant across the load. So we have to use some voltage control method to maintain the constant voltage across the load. So we use sliding mode control And a supercapacitor is also used to connect instantaneous change in the load. So it will be supported by the energy from the supercapacitor, especially for motor loads. So this is another figure just to show the charging and discharging of the batteries and how the power is maintained constant. So this is the third one, which again we tried in our lab, solar PV based DC microgrid system. So what we did, we had solar PV and then energy storage. So we just try to connect simply to a AC load PV, and then through a bidirectional DC-DC converter, we try to have this battery storage interface for the to make a load leveling, right? This is the test system, again, data and something we implemented, charging and discharging modes. All these figures are there to see the performance of this operation. So I am not explaining this. It can be understood. Win mode 1, multiple ESS, buck mode, boost mode, all those modes are there. And this is exactly the experimental setup which we implemented. So we can see this, the bottom one is actually the solar PV. And you can see it's a complete thing. This is the project we did in our lab. Neither we have actual load nor we have actual solar. So we use a solar simulator. This is from Agilent. Then load bank, load from this Chroma load, electronic load is there. So solar and load both are there. You can see in front of you. And then this is the ESS battery, and this is DC link capacitor, and this is the complete converter to make this DC microgrid. And you can see this all happening with the help of this DC interface. Okay, another very important aspect of this microgrid and high power grids are the solid state transformer. So conventionally, as we all know, we need a AC to AC transmission, AC to AC transformers. So we have AC to DC and then DC to AC through power electronics transformer that we call solid state transformer. So this can be used is a 2-stage and this is a 3-stage SST. And you can see this is what high frequency dual active bridge can act like a core processor in a SST. And this could also be a useful thing in a microgrid whenever you need to actually transfer power from one voltage level to other voltage level. So SST can play a role. This is again one structure we tried in our work in our lab, that is with a 3-phase AC to DC converter. From main 3-phase grid, we use 3-phase converter first of all, AC to DC. Then we use from DC to DC using a dual active bridge that we implemented in the lab. And then we use DC to AC converter, inverter means, for driving the loads like AC bus with the AC microgrid, and this is the DC microgrid. So you can see this is what we are doing, trying to do that AC DC both microgrids are there, but it is interfaced to the main AC grid through a solid state transformer. So that's a very simplified representation. That is the AC grid, SST, then AC microgrid and DC microgrid. So you can see this is what we tried in our lab. And this is exactly the structure with a 2-bridge parallel connected dual active bridge, because one of the requirement is that the DAB is using the MOSFET switches, so it will be difficult to transfer the high power, right? So in order to transfer the very large power, you may need parallelism of dual active bridge for DC-DC power transfer. So you can see here that these are the structure exactly I mentioned, and then we try to implement. You can see this is actually the SST. This part is actually the SST part for a high power SST, you can say. And then this is a DC to AC inverter, and the DC bus of this will be used as a DC microgrid, and AC bus will be used for AC microgrid. So that's what we actually did, and this is what our laboratory setup, which we have done in our lab here. So this is grid interface connection. This is interlinking converter, and then yeah. So I mean, this is one of the things which is very much upcoming, and I feel that it may be useful for. I mean, SST, something I don't know how much it will be reliable in the future, but this will be current. I mean, this is also a very important area of research, especially for low and medium power transfer, right? So in a microgrid, again the issue comes actually if it is grid feeding mode. So you have to interface your AC/DC microgrid with the main grid, and then a main grid connection with these microgrids need efficient transfer of the controllable power. Right? Because every time you have to be, your power need to be controlled. So dual active bridge is a kind of a this thing device which helps actually the controlled reactive and active power, especially the controlled active power. Right. So this is a typical topology. This is a typical topology which you can follow for implementation of both AC and DC microgrid application. Right. Typically a hybrid AC/DC microgrid application. Right. So and I was just trying to illustrate some of the components I would like to identify. Although this is done by one of my PhD students. You can see this is the IPM, we call Intelligent Power Module, IPM. It is actually a three-phase converter, so you can use it as a three-phase inverter. And this is dual active bridge. This is dual active bridge. This is bidirectional converter. This is, you can see the 4 driver circuit. Basically, the 4 driver circuit are used for, if you can see this, the 4 driver circuits, 4 bridges rather, 1, 2, 3, 4. So what we actually done, if you have a 2 lines or if you have a bulk of power, it can be divided into the 2 legs of the bridges. So it's kind of a parallel connection of it to DAB, dual active bridge. So this is one DAB and this is another DAB, right? And both are connected in parallel, right? So if you have a large power, right, so you can transfer this large power through the parallel connection of the bridge. And this white part is actually the high frequency inductor. High frequency transformer, sorry, because this provides the isolation between main grid and the microgrid. So one very important aspect in this whole scenario is that if you are connecting your microgrid to the main grid, it should be preferably isolated. Now, if you use typical transformer, right, for isolation purpose, microgrid and a main grid, Remember, this is a very useful point and important point. If you are interfacing your microgrid with a main grid through a conventional transformer, think of the size of transformer. If it is suppose 100 kVA microgrid, so you have to connect a 100 kVA transformer, low frequency transformer, 100 kVA. Think of a size. It will be something like a transformer which is there in your society, right? You don't want that. There is the role of this dual active bridge is also to use a miniaturization of a circuit. So if you use DC to DC converter, you can use high frequency transformer, which is very, very small size, very, very small size, right? And that way you can save the space and improve the efficiency and make the circuit compatible. Okay. So high frequency transformer, you can see the whole thing is about 1 kVA or it can be about 2 kVA because we have 2 IVDC. And see the size of this transformer, which is not only providing the stepping up or stepping down, but it is also providing you the isolation between microgrid and the AC grid, the main grid. Okay, so that's what very important thing. Then you can see these two are actually the again the circuits AC-DC converter. Right, you have a main grid. You can see here you have a 3-phase step-down transformer. 3-phase AC grid is there. It's coming from here. You can see the 3 set of wires. It's coming in the 3-phase transformer. 3-phase transformers you can see is getting transferred. And we have 2 circuits. One is through this. You can see this grid interface converter. This is grid interface converter. And this is another grid interface converter. So exactly the link which I was mentioning, the 2 links are coming with the 2 separate grids or maybe the same grid. In this experimental setup, we have used the same grid, but it may be from 2 different grids also. From that point of view also, it is very important that you should have a good arrangement of the sections. And then you have a whole thing controlled through what we have done. We have controlled whole thing through LabVIEW based programming, that is through NI software and hardware also. So we have used FPGA 7813, I think, FPGA PCI controller for operation of the complete control action of this SST based system. So I hope, and these are the DC link capacitors. You can see here, these are the DC link capacitors. And these all are the MOSFET switches because it is up to 2 kVA operation. So we have used these inbuilt systems for making it MOSFET based. Another Spartan FPGA processor. So overall, yeah, very, the huge setup. Now this is what the glimpse of future microgrid or a smart grid, whatever you say, right? You have a wind system, you have this solar PV system, then you have a control center, right? Then your buildings are like smart buildings, which is capable of net zero emission or net zero building we can call, e-governance and so many things. And that's how we can achieve our net zero emission by 2070. Okay, and you have EVs, which needs smart transportation for charging and discharging, right? So thank you very much. That's what I wanted to present. I just tried to finish well within time so that we have enough time for any kind of discussions or questions.
Thank you, Gupta sir. Thank you, Professor Gupta sir. And participants, if you have any query, you can directly interact. It is a wonderful opportunity to all of you to interact with Gupta sir directly.
Yeah. So,
participants, if you have any query, you can write in the chat box also. I will ask your on behalf. This was actually afternoon. Just lunch
I know. After lunch sessions are always very boring kind of sessions, and everybody feels sleepy. But still, I touch so many topics, and if anybody has any keywords also, I can explain. Not a problem. For anything to be useful for your students or your own research work, I would be happy to share my experience or my expertise.
Hello, participants. Participants, you just raise your hand. We will unmute you. We will unmute you. You will directly ask the question. First, you raise your hand if you have any query, please. Okay, I think so. There is no question in the chat box also. No issue.
Okay, not a problem. I am as a professor in the Department of Electrical Engineering, and my email ID is also there in my website. So at any point of time, if anybody have any question, you are welcome. You can come MNNIT also. We are also running some of the short-term courses very recently. We are organizing one of the conference. Let me share this, take this opportunity to interact with you all. We are organizing one of the conference which is called Student Conference in Engineering and System, SCES 2022. This is the 7th version of the conference. So if you are doing any research along with your student, please encourage your student to submit the paper. The last date of the paper is 1st March, but we are going to extend another 15 days. So any kind of research which you along with your student are doing, please convert it into the form of a paper, and it's a very good opportunity for you and your student. And similarly, we organize many other short-term courses, and if you are interested, you can directly talk to me also, and you can drop mail also to me. At the moment, I am also acting like a head of the department. So for any other query, you are welcome. So what
now I would request Professor P.K. Shah sir to give the farewell remarks to Gupta sir.
Thank you, Dr. Asutosh Giri sir. On behalf of the GC Bharuch and the STTP Organizing Committee, we are very much thankful to Dr. Rajesh Gupta sir, Professor and Head of MNIT Allahabad, for this wonderful and very knowledgeable session on DC-AC hybrid microgrid for low power distribution system. Let me very briefly summarize the session conducted by Dr. Rajesh Gupta sir. Dr. Rajesh Gupta sir has spoken about the DC microgrid, AC microgrid, the hybrid microgrid, various architectures and configurations, various case studies and test systems, experimental results, etc. So beyond that, he has also given an open invitation to all of us to be associated with the email address, etc., for any future queries, etc. So we are very heartily thankful to sir for very enriching session. Thank you so much, sir, for accepting our invitation. and very good session on this topic. Thank you, sir.
Thank you, sir. Thank you so much for you.
Thank you, sir. Namaskar. Thank you very much. And
very
hopefully we will meet in the month of June.
Sure.
Thank you, sir.
और मेरा रिक्वेस्ट है, मैं आपको लीफलेट भेजूंगा कॉन्फ्रेंस का, आप अपने ये जो भी ग्रुप है उनको भेज दीजिए.
जी बिल्कुल सर, we will definitely contribute.
Yes, sure. Thank you so much. Thank you.
Even in NITs also, I will circulate in NIT Surat as well.
Yes. That will be good. Thank you.
Thank you very much, sir. Thank you. Thanks for joining. Thanks. Okay, dear participants, now third session will start sharp at 3:45. And before that, you can enjoy your tea and snacks. And then we will again join at 3:45 for the third session and last session of this day. Again, I am requesting you, don't worry for the attendance. There will not be any separate link for the attendance. We are directly downloading. Just I am showing you how I am managing the attendance. Just you can see here, because all are connected. That's why I am just showing you one glimpse how we are managing that online attendance. You just see here. I am showing you. I think so. You all are able to see this screen, right? And now just you see here participants and then download attendance. Directly attendance is downloaded. If you are entered in the session, if you have joined the session, your attendance is downloaded and it is coming in my download list directly. Just you see, attendance is downloaded. This is the meeting attendance. See, all are here. The people who have joined us, and when they joined, when they left, when someone joins, when someone left. It is very transparent system actually. Nothing is hiding in this software. You don't worry for the attendance. I am trying my level best to make you happy here, and definitely my support will be there unless you are attending the classes and sessions. Please attend the sessions very regularly. Make your 100% attendance throughout the session, because we are downloading this kind of attendance at any time. Suppose session is started at 10:30. I am going here at 10:45 or 10:50 or 10:55. That means no fixed time. Randomly it is downloaded from this directly. And if you are not there, you will be considered as an absent. And if you are there, definitely your name will be there. So my request again and again is the same. Attend the session very regularly. Yes, someone is raising the hand. Unmute him. Yes, unmute yourself now. Doctor. Someone has raised the hand.
Yes, Pooja Joshi ma'am. Just unmute yourself.
Yeah, Dr. Pooja Joshi.
Good
Yes.
afternoon, sir. I have a question regarding to your attendance. Sir, recently our GTU examination is going on. Okay, so maybe there are some issues regarding to attending the class whenever we are in examination time. So we cannot deny our examination due to which are given from the GTU. So what happened when we are in the GTU examination? Because you are saying like that, okay, you are attending, attendance will be downloading at any time. So in between that section, suppose the paper was started from 10:30 to 1:30. Is a basic regular time. Okay, so if we are not suppose as we are in junior supervisor or we are in senior supervision duty, the phones are not allowed. So what time that we have to, what kind of the?
Yes, I got the question, and thanks for asking the query. But the thing is, this is not the MOOC course, madam. we are running the live sessions in the
Sir,
MOOC
we are
courses.
also attending many of the FDB which are followed from the FDP, sir. But we cannot deny the duty of the GTU, sir. I think you know very well that thing, sir.
Have you taken the permission from your concerned authorities to attend the session?
Yes, sir, I am taking, but sometimes the
interactive. Nobody is asking any question, not writing anything on the chat box. It is totally going blank. It is better if you keep the sessions interactive by asking the question. You are encouraged to ask the question. From tomorrow onwards, I will allow your mic and your camera both. You can ask directly, but today you can raise your hand if you want to ask something. And you will ask the questions only when you are listening carefully. That is also one truth. If you are not attending the sessions sincerely, then it is difficult to ask the question as well, because you are not getting anything, then what to ask? Make the sessions interactive. Attend the sessions with full sincerity and make the sessions interactive by asking the questions. Because some experts are also feeling like if you are not asking question, they feel like you are not listening them. Yes, expert has joined, Dr. Sabir Bohra. Just I am admitting him. Yes, Dr. Bohra sir has joined us. And hello, good afternoon, Bohra sir. Hello, Bohra sir. Hello. Are you able to listen me, sir? Dr. Bohra sir. I think so. There is some problem in his audio. Dr. Bohra sir, please unmute yourself.
Muted है sir. Muted है.
Muted है, but Dr. Bohra sir, please unmute from your end. Hello.
गिरी सर फोन कर दीजिए.
हाँ सर, आप ज्वाइन हो गए क्या? अच्छा अच्छा, ओके, ठीक ठीक है, ठीक. ऐसा है, हाँ हाँ, कोई हाँ, यस यस, ओके, नाइस. बोरा सर ज्वाइन हुए? Yes. Hello. Dr. Sabir sir, you can unmute yourself.
Hello.
Yeah. Now you are available, sir. Thank you.
Okay, fine.
And let me introduce our eminent expert to the participants. Yes, today we have a very distinguished guest, Professor Sabir Bohra. He is a professor and head of the Department in Electrical Engineering, Sarvajanik College of Engineering and Technology, SCAT, well-known word in the South Zone of Gujarat, SCAT, India. He has worked as a visiting researcher in Department of Energy Technology at Aalborg University, Denmark. His research interests are renewable energy sources, energy management, grid interactive PV system, hybrid microgrid, and power quality. He received his bachelor degree in electrical engineering from the SVNIT Surat in 1999 and master degree in energy system from the IIT Bombay. He was awarded PhD in modeling of advanced silicon solar cells from the SVNIT Surat in 2015. He has authored and co-authored many technical research papers in peer-reviewed national and international journals of high ranking. He has been associated with many solar photovoltaic and energy management projects. He has been working as an energy auditor and consultant since 2010. And sir's contribution in the area of electrical engineering is enormous. And I hope so the participants will enjoy the sir's session. He is going to take the session on the Homer based modeling of the distribution, that means microgrid. I will not take much time. I would like to hand over the session to directly Professor Sabir Bohra. Thank you very much, sir. Thank you for joining us. And I hope so session will be interactive by the participants. Thank you very much. Now you can start, please.
Hello. Thank you very much. Thank you very much, Dr. Ashutosh. Is the slide visible?
Yes, sir. It is visible.
Okay. A very good afternoon, participants. Today we'll be discussing on the power quality and reliability issues for the distributed energy sources in microgrid FDP. And specifically, I'll be discussing something about the planning of microgrid, some relevant issues of the microgrid, and mainly we'll discuss something on the microgrid planning application tool, which is a Homer. Okay, so we'll be focusing on that. And I'm just turning off my camera. So whenever you have any query, please let me know. And whenever you feel interruption in presentation or when the slides are not visible, please let me know. Okay, so let's start with the topic. I hope some basics things might have been discussed by other speakers from the morning or so. So we'll be discussing something about this, the introduction and connection between the microgrid and COP26, some fundamental definitions and understanding of the microgrid, some features of the microgrid, population of the microgrid, classification of the microgrid. Some will be taking some examples and examples of planning about the microgrid, and I'll discuss one of the papers details which was simulated and analyzed using the Homer for the microgrid. Okay, so this would be the outline of the presentation. See, whenever we are talking about the planning of a microgrid or any system, we should know the requirement of that particular project. I'm taking this as a project. So what is the requirement, how it is beneficial to the society, how it is what would be the impact on the environment and all those things. So that's why I'll try to relate some other topics also. I mean, they are related, they may be loosely related, they may be tightly related with the topic of the microgrid. Okay, so basically the theme of the FDP is the power quality and reliability issues, but unless and until we have a strong planning and the structure of the microgrid, it is very difficult to anticipate about the reliability and the power quality issues. Okay, so I'm just trying to correlate those things with this particular presentation. So COP has some highlights of the COP 26 Glasgow, which was recently taken place. So it can be considered as one of the most anticipated and the biggest international summits regarding the climate action and the climate change. The focus area of the conference was to devise a global net zero plan and need to control the rise in the temperature, which is taking place globally. This agenda has been signed by most of the countries like US, India, EU, China, developing countries and other developing countries, and some of the nations considered to be the most vulnerable to the climate change. And out of those so many countries, 23 countries, including the world's top 20 coal-fired power generating countries, have made the pledges to phase out the coal power. That some of you might be aware or the familiar of. India is currently holding the 4th rank in the installed renewable energy. And there are 5 points resolutions that we were taken that bring its non-fossil based energy capacity to 500 gigawatt by 2030. By 2030, fulfill about 50% of the energy requirements and the consumption through the renewable energy, cutting down its net projected carbon emission by 1 billion tons, reduce carbon intensity of its economy by more than 45%. And by 2070, India would like to become a net zero country. Okay, so these are some of the highlights that we discussed. What exactly the microgrid is? In 2004, the microgrid was defined as a better way to realize emerging potential of the distributed generation in a systematic approach, which views generation and associated loads at subsystem. There are different definitions, but the crux of the definitions are the same. Microgrid concept was firstly introduced by a consortium for electric reliability technology solutions, that is abbreviated as CERTS, to reduce the cost and increase the quality of the power. DOE Microgrid Exchange Group, that is DOE-MEG, defines the microgrid as a group of interconnected loads. There are a number of interconnected loads connected, and they are powered by distributed energy sources within the clearly defined electrical boundaries that acts as a single controllable entity with respect to the grid. So if you take a grid as an entity, then this microgrid part needs to be treated as one of the entities. Okay, that could be a number of microgrids connected, but one cluster should be treated as a microgrid. It can be connected and disconnected from the grid to enable both grid connected and islanded operation. A small scale localized station with its own power generation resources and loads, as well as definable power supplying boundaries, qualifies as a microgrid. Okay, so it is basically a cluster of having the number of resources, number of energy sources, the number of loads. They are connected and they are controlled independently. Okay, if they are not connected with the grid, then they are controlled independently. If they are connected with grid connected system or the utility grid, then the grid is having some control over it. Okay. What are the different features in general? The microgrid can be classified as a microgrids are electricity distribution system containing loads and distributed energy sources such as distributed generators, storage devices, or controllable loads that can be operated in a controlled, coordinated way, either while connecting to the main utility or while operating in islanded mode. So it is a flexible and dispatchable system. It can be grid connected, it can be islanded or standalone system. Microgrid could be a grid connected one, or it could be a standalone system. It can potentially reduce the dependency of the consumers on the traditional generation system by providing different types of energy such as electrical and thermal, and provide ancillary service trading activity between the microgrid and the main grid. So it could be interacting with the main grid, it could not be interacting with the main grid in islanded mode. And what is the main feature of it? It reduces the dependency on the main grid. So even if in the case of the non-availability of the main grid, the cluster would not stop working. Okay, it remains powered by its own local sources. So there are some loads which may be treated as a critical loads, and some loads which may be treated as a non-critical loads. So the non-critical loads may be cut down, but the critical loads will be powered by the microgrid and the local energy sources. So the configuration could be AC, it could be DC, or it could be hybrid microgrid. Okay, it could be purely AC microgrid, it could be purely DC microgrid, it could be a combination or a blend of AC and DC microgrid. One of the significant reasons why developing countries adopt the microgrid solutions is to solve the problem of the rural electrification. So this is the main advantage of establishing, developing, installing, planning of a microgrid. So in the rural areas where it is not possible to lay or to develop or extend the utility or the grid transmission, then at that point it would be comparatively cheaper or inexpensive to have the local generation for the local consumption of the load, or to cater the local loads. So they are the localized groups of the interconnected and distributed energy sources. It comprises of generators, multiple generators, distribution systems, and sophisticated controls. Offer number of benefits like the grid resiliency. The grid becomes unstable in some of the cases, so it provides a grid resiliency, improved power quality, which is the theme of the course, and the low impact on the environment, and thereby leading to the increased demand. So it would also help in achieving the less carbon footprint. Apart from that, the growth of the segment can be attributed to the expansion of the utility-based grid networks globally, coupled with the large-scale harnessing of the renewable energy sources, including the offshore winds, and can be used as a backup or the supplementary power sources for the main grids. Okay, it may be assisting, it may be backing up the grid. Global warming and the growing energy demand are the most significant drivers. As you know that day by day the energy demand is increasing, electricity demand is increasing, and in order to meet the demand, it is not possible to increase the generation capacity of the conventional power plant. Okay, so this is one of the options by which we can try to bridge the gap between the load and the supply, or demand and the supply. Are the most significant drivers spurring the renewable energy sources to reduce the greenhouse emissions by the fossil fuel based electricity generation. Distributed energy sources like the photovoltaic modules, wind turbines or wind based generation, combined CHP plants or the combined heat and power units, controllable loads like electrical vehicles, which is one of the most emerging areas in the country, and the other developed countries as well, are expected to play the considerable role in the future electricity supply. Just to give you a number, and approximately 8,300 terawatt hour of the electricity was generated from the renewable energy sources in 2021, and which is around that 1/3 of the total generation capacity. Okay, you can get more details. I have already written the site URL. So you can get more details, and it is almost around 32-33% of the total generation, as it has been mentioned that 1/3 of the total generation. So that is 8,300 terawatt hour of the units are being generated through renewable energy sources. What are the benefits of that. So the carbon emission reduction, energy efficient enhancement, power quality and reliability improvement, line losses reduction, increasing power transmission capacity, especially in DC microgrids, deferral of the grid expansion or delay of the grid expansion plans, requiring fewer technical skills for operation, relying more on the remote control and automation. There is nothing like a free lunch, so that also comes with some challenges. So renewable energy sources such as wind and solar are highly dependent and on weather conditions. They are intermittent in nature. It is difficult to predict, though there are some algorithms which predicts quite well. But even though they are unpredictable, they are sensitive to unpredictable changes. The small generation. The uncertainty of the islanded microgrids is much greater than that of the utility grid. It is having a low inertia compared to the very large or the huge grid connected system. One of the major challenges faced by the microgrid in the islanded mode is maintaining the balance between the generator and load continuously. Because there, in case of the grid connected system, when we have a surplus amount of the power, then the surplus power we feed into the grid, and when we are having a deficit of the generation, then within that cluster or the microgrid, then what we do, we import the power from the grid. So in that case, the balance can be achieved very easily. But in case of the islanded or independent or the standalone system, it is sometimes very difficult to manage the generation and the load, because sometimes the load may suddenly change. You cannot change the generation suddenly. So that is one of the major challenges. Regulation, the current regulatory framework was not designed to incorporate the DER or the microgrids. Some of the common grid services provided by the energy storage devices are categorized as a power quality, transient stability and regulation services, spinning reserve, voltage control, arbitrage of energy, load balancing, congestion relief, firm capacity, and upgrade deferral. So apart from this technical and regulation challenges, we have economical and marketing challenges also. So despite the advances in technology, the investment cost remains very high in microgrid. And the cost of the storage system, some of the DGs like the photovoltaic and fuel cells are still they are very expensive and may not be affordable by the area which we would like to be electrified. Efficient energy management system needs to be developed and adopted. As far as the marketing is concerned, the microgrids can participate in market by selling their products and services. In this case, in terms of the electricity, can also play an important role in developing free local energy markets by encouraging users to install their own distributed energy sources, offering new services and supporting self-consumption. So anybody can install their own renewable energy sources like the rooftop photovoltaic system. You may be, if there are some countries where you have your own wind turbines to meet your own demand. Daniel of the local energy trading among the DG and demand and microgrid market positioning difficulty. The statistics by the International Energy Agency, that is IEA, I have taken some of the references from the IEA itself, predicts that there will be a tremendous increase in the development of the microgrid by 2040, and about 80 million people will have access to the electricity through the microgrid. Okay, so this is the projection by 2040, and it is expected that around 80 million people can get their electricity by the microgrids. So this is a very typical structure of the microgrid. I hope those who are the participants in this course, they might have some basic understanding of what the microgrid is, what it consists of, and all the certain relevant aspects. So it has been presumed that they know something, but there are some participants who may not be well familiar with the structure of the microgrid. So very briefly, I'll be discussing those things. So this is a typical structure of the microgrid. It consists of the loads, as we had already discussed. It may be communities and institutions. The load may be commercial and industrial, the loads may be residential, then you may be having a very huge load of electric vehicle charging stations, then you have a combined heat and power, then you have a conventional generator, energy storage device. It doesn't mean that you have a battery only, you have different kind of energy storage devices. You have renewable energy generators like the wind turbines, photovoltaic systems, and you have the utility or the grid connected where the microgrid is connected. And this everything is being managed by the microgrid controller. So how much amount of the power is to be imported or to be exported with the utility, or transaction of the power and energy between the utility and the microgrid structure, that everything is the care is being taken by the microgrid controller. Now, as I have already mentioned, that there are three types of the microgrids. One is the DC microgrid, one is AC microgrid, and the third one is a combination of the AC and DC microgrid. So here, this is an example of the DC microgrid, where you can see the main bus is operating at the DC level. Main bus is operating at the DC level. So if this is the DC level. So this PV is generating DC power, and through the converter it is again connected with the DC bus. In case of the wind turbines, it generates maybe the DFIG may be there, maybe some other kind of the induction generators are there. So they are generating AC at the different frequencies, but then it is getting rectified and is connected with the use of the converter with the DC bus. As you can see over here, some loads may be AC loads, some loads may be DC loads. So AC loads are getting powered by the DC to AC converter. The DC loads are getting powered by the DC to DC converter to have the voltage matching, because the bus may be operating at the different voltage and the load may require a different voltage. The bus may be at 110 volt, 48 volt, something like that, but your load requirement is 12 volt, 24 volt. So in that case, you need to have the a converter arrangement. Similarly, there is a charging station, there is a storage unit. This capacitor indicates there's a storage unit, a super capacitor or the ultra capacitor arrangement. Then you have a energy storage unit like the battery energy storage system. So this is a typical structure of the DC microgrid. And apart from that, it may be connected with the utility also. So utility is operating at AC, and then you have the AC to DC converter in order to have the interface with the DC. Then you have AC microgrid and DC microgrid. In this case, you can see that the AC microgrid does not have any connection, any electrical connection with the DC microgrid. So traditionally, we have AC microgrids like this. So we have all the AC generators and AC sources, where we have DC generators like PV. We invert it and we connect it with the AC bus. And here it is a DC microgrid, as we had just rightly discussed. Okay. And the third option is the AC-DC or the hybrid microgrid. So in AC-DC microgrid, you have both buses running simultaneously. You have AC bus, you have DC bus. You have AC generators connected with the AC bus. You have AC loads connected with the AC bus. You have DC generators, those are connected with the DC bus, and DC loads are connected with the DC bus. Depending upon the requirement, maybe converter interface through the converter, without converter, that depends upon their voltage level and the bus voltage level. So according to one of the reports, there were already 4,475 microgrid projects all over the world. And these microgrids sum up to a whopping of around 27 gigawatt of the total installed capacity. Total microgrid market is estimated to grow from $24.6 billion in 2021 to around $42.3 billion by 2026 at a CAGR of 11.4%. The growth of the microgrid market is driven by many factors like rising focus on decarbonization, growing adoption for the microgrids for the rural electrification, and rising instances of the cyber attacks on the energy infrastructures. Then initiatives by the governments of the different countries to encourage the development of the microgrids are also fueling the growth of the market. And around 22 intriguing microgrid or interesting projects in 22 can be accessed through these links, where you can get the different very interesting microgrid projects, upcoming projects in 2022. So the link is already given to you. These are some of the case studies. One is the Bright Indonesia, second is the Power Africa, and third is the Smart Power India. Indonesia, as we know, that it is comprising of the number of islands, and over the 88% of the Indonesia is now electrified. Okay, 66% of the Indonesia used to have the electricity, and now using this concept, over 88% of the Indonesia is being electrified. And that is because of this program, which is known as the Bright Indonesia. The goal of the Indonesia is to provide 1 gigawatt of the electricity to over 12,000 villages, where the electrification is needed the most by 2019. Second project is the Power Africa, which is also known as Beyond the Grid. And in this case, the Beyond the Grid is an initiative of the United States government to make the 30,000 megawatt new and clean electricity available to over 60 million African households in the remote and rural regions by 2030. And according to the latest report, the program has about 56 power projects which are already generating this much amount of the power. That is 3,481 megawatt of the power connected to 14.8 million homes and the businesses. Smart Power India, it was launched in 2015. And the program aimed to provide the renewable microgrid solution to at least 25 million Indians across 6 states. And in the latest reports, the Smart Power India had over 160 microgrids solutions spread in 4 major states like Bihar, Uttar Pradesh, Odisha, and Rajasthan. And microgrids were over 80% solar power, and their capacity ranged from 10 kilowatt to 70 kilowatt, and more than 70,000 people in the remote areas of the India are now having access to the sustainable electricity. Not only electricity, but the sustainable electricity. If you talk about the future in India, India is largest integrated power company, that is the Tata Power, plans to set up 10,000 renewable microgrids by 2026. So you can imagine what is the potential of the new microgrids. They are planning to have 10,000 renewable microgrids. Renewable microgrids means it is comprising of the renewable energy sources and not the conventional energy sources. More than double the number of the microgrid projects identified in the world today. Tata Power formed a new company, that is the TP Renewable Microgrid, to build, own and operate the microgrids, and will add to the 10,763 megawatt of the conventional and renewable generation that the Tata Power owns and operates in India, and it is serving around 2.6 million customers in Delhi, Ajmer, and Mumbai. So till now we have just seen the history and the projection of the microgrid. Now it can be classified in the different categories, like by type, by size, by application, by mode of operation. So it could be, if you look at the by type or according to the type of the microgrid, then it could be a campus microgrid, it could be a military microgrid, it could be a residential microgrid, it could be a commercial, or could be an industrial microgrid. So if a campus is planning to have its own microgrid, the campus may going to set up its own solar photovoltaic system. If the potential of the wind is sufficient to spin the wind turbines, then can have its own wind machine. If there are some wastage, then can have their own biogas generation, and so on and so forth. And if there is a requirement, even can go for the storage system. So that is a by type of the classification. Similarly, it could be valid for the military application, it could be for the residential application, it could be for one household, or it could be a group of households. It could be for one house, or it could be for a colony or something like that. Then depending on the size, the small and simple, about hundreds of kilowatts at low or medium voltage, supplying just a few customers. And second is a very large and the complex one, which is catering or supplying megawatts of the power. So it could be a very small. There is one more concept of the microgrid, which is also known as nanogrid. So it is very difficult to draw a demarcation line between this nanogrid and microgrid and so on. But basically the size matters. If it is very small in terms of the fraction of kilowatts or some few tenths of the kilowatts, then it can be treated as a nanogrid. And if it is extended to hundreds or thousands of the kilowatts, then it could be termed as a microgrid. Otherwise, they are structurally they are similar. Then by applications to provide the premium power or resilience oriented services. And second is the ability to withstand and recover the high impact low frequency events like the attacks, naturally occurring incidents, so on and so forth. So they are the special kind of the microgrids which are having their own specific applications. Then, as we had already discussed, by mode of the operation, it could be grid connected that exchanges power with the upstream grid and the islanded due to the faults, or it may be planned or unplanned. The system, the microgrid actually is a grid connected one, but because of the planned or unplanned maintenance or because of the poor power quality, the entity isolates itself and then it becomes the islanded or the standalone system. So it may face challenges in regulating the voltage and frequency when it is connected with the grid. Then there is no question of the variation in the frequency and the voltages, because ultimately that is derived from the grid. But when it becomes independent, then there is the issue of the controlling the voltage and the frequency. Then by configuration, the loads, micro sources, and the storage devices are integrated, lead to the different configurations like we had discussed, that AC network, microgrid distribution, single phase, it could be single phase, it could be three phase with neutral and three phase without neutral, DC microgrid. It is for the emerging kind of the sources and loads. It could be monopolar, bipolar, and homopolar. Then if it is a combination of both AC and DC, then it is a hybrid microgrids. Then apart from that, from the feeder configuration perspective, it is urban feeders are located. If the urban feeders are located in the congested industrial area, then it offers a low imbalance degree because of the short distance and may experience the low voltage drops. And in contrast to that, the rural feeders are placed in the populated area, and the distance between the main body and the others are fairly long or fairly far from, because of the scattered nature of the loads. Then the voltage profile would definitely be non-flat. And off-grid in an islanded mode, remote area, large size distributed energy sources integration. So these are some of the categories or the classification of the microgrids. So may I have any question if till now? Am I audible clearly? Are the slides clearly visible?
Yes,
it
yes,
is
sir.
Fine.
Everything is working fine, sir.
Okay, so we'll move ahead. So now let's come to the point of the discussion. Up till now, it was just a background. What is the requirement of the microgrid? What is the microgrid? What are the kind of the sources? What are the classification? What is the demand? What are the benefits, advantages, and drawbacks of the system? Now, when we are planning to have a microgrid, then what are the different stages? I'll just try to correlate this with the application software. So planning stages of the microgrid. So usually it starts with the defining of a problem, then identification of the requisites, then deciding the objectives. What is the objective? The objective could be the type of the microgrid, what kind of the microgrid that you are going to set up, exploring the feasible alternatives. Sorry, it was examination bell ringing, and deliberately I muted it. So exploring the feasible alternatives, what are the possible available alternatives that needs to be explored, and then enlisting the assessment criteria, and then it needs to be fed to the selecting an application of the decision making tool, and verification and a validation. So these are the different stages of a planning of a microgrid. Typically, it is also shown for one of the methods that is being adopted by many researchers, and not only for the technical, but it could be for management, it could be for procurement, it could be for selection of the right candidate, it could be for selection of the students, it could be for the performance analysis of the employee, and so on and so forth. It could even be for the selection, the best site selection for hotel. It could be for the best site selection for the restaurant, for resort, etc. So in that case, what is to be done? First you have to identify the problem and its nature, then prepare the hierarchical structure of a problem's evaluation. Then you have to select the one of the methods, that is MADM, that stands for the multi-attribute decision making system, and collect relative weights or score for each criterion for each alternative. So you may be having the number of alternatives available with you, and each alternative is having a number of criteria. So that needs to be scored, that needs to be given, that needs to be assigned the weights. Determine the best alternative based on the aggregated values of the relative weights corresponding to the chosen alternative. Like a student is having number of subjects, and he or she is giving more weightage to subject A than subject C. So obviously he or she could score well in subject A than subject C. So is giving more priority to subject A means it's more weightage is given to it. So likewise, you have number of alternatives, and you have each alternative is having the number of criteria. So that is the main point of the discussion. Planning of the rural microgrid, basically, as we had already discussed, that where we can extend, where we have availability to expand the utility grid, there the microgrid concept is less important, unless and until you are very keen about, very aware about the carbon footprint, greenhouse gas emission, environmental friendly generation, etc. So it is mainly for the rural application, where it is very difficult to reach, where the population is still, where many people are still living without electricity, without even having access to the electricity. So microgrid planning is a very complex problem, and that involves what are the challenges that we had discussed. So all those challenges are included over here. It could be technical, it could be economical, social, environmental factors, optimal utilization of the sources, least overall cost, resiliency and reliability, and even the power quality issues. So see, when power quality issue comes, when there is the availability of the power. If you do not have the availability of the power, then there is no question of the power quality. Okay, first you have to get the power, and then the power quality issue comes into the play. And the recommendations from the various literature are categorized in these ways. One is the strategic planning, the operations, and the social context. The strategic planning, that a group's a set of practices that reduces uncertainty and the risk for the developer, including the market and supply chain assessment, technological choices, and government policy. Operations has the cluster technical, commercial, financial practices, and the social focuses on the activities relating to the community involvement and the services. What is the optimal planning for the microgrid? What exactly is the optimal planning for the microgrid? What should we look when we are going for the planning of a microgrid? Only the economical aspects, technological aspects, or the technical aspects? Should we use a very advanced technology? That is the objective of the microgrid. Should the cost of energy be as least as possible? That is the objective. Should it have the least carbon footprint? That is the only objective. So there are different objectives of the microgrid, and we cannot focus, we cannot target, we cannot consider only one aspect of the microgrid for planning. It should be multifaceted, it should be holistically designed one, and the two principal economic elements, which are the total net present cost, that sometimes it is also known as NPV or NPC. So here we are talking about the net present cost, not the net present value, like we used to discuss in case of the investment markets. And the levelized cost of the energy, that is LCOE or COE, that depend on the total annualized cost of the system. Because of that, the user needs to calculate the annualized cost of the system, which is the components annualized cost minus the miscellaneous cost. This case study is given for one hypothetical rural community, which is having 5,000 units per day of the consumption and around 1183 kilowatt of the peak demand. The thermal load is considered that the 5% of the electrical load, and scaled annual average is 500 units per day, while the scaled peak load is 51.07 kilowatt, and the load factor would be around 3.36. If you look at the solar resource, the annual average solar radiation for that particular region is considered to be 3.64 units per meter square per day, and wind resources average wind force particular that area is 5.78 meters per second. As we are a bit familiar that some minimum kWh per meter square per day is required to have the economic or the feasible installation for the solar irradiation, the solar based system, and the wind energy should be around 5 to around 8 or 9 or 10 meter per second to have the sufficient generation. Diesel price prevailing in that particular area is $1.17 per liter, or around 89 rupees per liter at that time when this was published, and with an emission density of the 820 kg per meter and carbon content of around 88% and the sulfur content of around 0.33%. System economics is the annual real interest rate is considered as 0.6%. The real interest rate is equal to the nominal interest rate minus the inflation rate. So please don't get confused with the bank interest rate. And the project lifetime is around 25 years. Okay, so I'll just show some snaps of the researchers, those who have already done in the homework, and then we'll switch over to the some real example of the homework. Okay, and some snapshots of the homework. So homework is one of the tools for simulation of the microgrid. And let me tell you one thing, that it considers only the economical aspects. It does not look into the other aspects like the social aspects, government policies, other feasibilities, acceptance by the locals, acceptance by the government. It does not look at the skill set available in that area. It does not look at the availability of the fuel. Maybe conventional fuel may be used. So these are some of the aspects which are overlooked in case of the homework, and it gives only the picture about the financial outcomes. So hybrid optimization model for the electric renewable, that is popularly known as HOMER, is a simulation tool developed by the US National Renewable Energy Laboratory, that is NREL, to assist in the planning and design of the renewable energy based microgrids. The physical behavior of the energy supply system and its life cycle cost, which is the sum of the capital and operating cost over its lifespan, is modeled using this HOMER. Where this details are taken is already been mentioned in the slide. So it was from optimal planning and design of renewable energy based supply system for microgrids, and it was bit older one, was published in 2012. What kind of the sources the authors have used? So the wind is being used, solar is being used, micro hydro is being used, battery is being used, converter, and grid extension is not that. And the price of the electricity was $0.14 per unit, and diesel generator was also employed in it. Okay, so almost all kinds of the sources are being there, and you can see that apart from that, the sources, the authors have used this boiler, this dump load, and the thermal load. So it considers that the thermal load means the heating kind of the load is also the one of the requirements of that. And these are the some different combinations that the authors might have tried. That is the 10, 50, 100, 500, and 1000 turbines. Similarly, the solar for 1 unit, 10 unit, 100 unit, 1000 unit, and 3000 kilowatts of units. Similarly, for the micro hydro, it is having the flow rate of the 500 liter per second of the flow rate, and so on and so forth. Okay, so that is one combination. Second, as we were discussing that thing, so the most critically influencing the criteria is economic, technical, structural, operational, maintenance, environmental, and the social aspects. They also need to be equally looked upon it. So in that case, you can use, you can club two different algorithms or two different tools. One is Homer and other is one of the MCDM techniques. So the model for planning of the energy sources for the microgrid using a multi-criteria decision making based on analytical hierarchical process approach. So here these two techniques are being blended. One is some outputs are taken from the Homer, and those outputs are then processed with some other technique. We'll not be going into this MCDM and AHP techniques because our main discussion is on the Homer and the planning of using the Homer. So the main utility grid as the primary source of the electricity alongside the conventional sources like diesel generator, gas-based combined heat and power with the absorption chiller to meet the cooling demand of the facility. And proven and comparatively most environmentally friendly renewable energy sources such as the photovoltaic together with the battery energy storage system. So while planning for the microgrid, these are the some of the criteria should be considered, and not only the economic or the financial parameters. So if you look at the economic issues, then the economic issues involves the initial cost of the equipment, energy cost, operational and maintenance cost, estimated internal rate of return. Now these four can be considered. This four or the economic issues or the criteria can be incorporated into the Homer, but the rest are not incorporated into the Homer. Some of them may be incorporated like the lifetime and so on, but not all are included. Then if you look at the structural issues, then it includes the footprint, lifetime, modularity, installation, lead time, annual performance degradation. When you look at the technical issues, then you may be having a very rich library in Homer for any kind of the sources. So you may select photovoltaic modules from X size to Y size, and from X manufacturer to Y manufacturer, and similarly for the case of the hydro turbine, similarly for the case of the biogas, similarly for the case for the wind turbine. And then technical issues like in-house and local technical skill requirements and availability, self-sustainability or the islanding features. So whether it is having the self-sustainable system or it can be islanded. What is the availability of the fuel and what is the capacity of the generation? Similarly, the other operational issues like the efficiency of the system, operational days per year. Now, if we go for the solar photovoltaic, then you cannot say that it should remain operational throughout the year or 365 days a year. It depends upon where it is being installed and what is the average irradiation at that particular place. Estimated energy production, force, outage, and reliability. Indirectly, it is related to the maintenance work and unpredicted shutdowns. What is the capacity utilization factor? What is the noise level? What is the CO2 emission at the pollution? CO2 emission of the pollution? What is the look or the aesthetics and elevation? What are the stakeholders' preferences? So these are the some qualitative aspects, subjective aspects, which also we need to take into account when we're designing when we are planning for the microgrid. Okay, so again, I'm not discussing some of the details in that because we have skipped some things deliberately. So after processing those things, you may find that the economic is having this much amount of the weightage, and then it comes the technical. And these are not the randomly generated numbers. These are numbers after processing through that algorithm. If you look at the particularly economic criteria, then initial cost plays this role, energy cost plays this role, internal rate of return is having this significance, and maintenance is having this significance. Similarly, the structural criteria, if you look at, then the lifetime in years is a very critical. Then comes the annual performance. Similarly, the technical criteria, generation capacity is very important. Operational efficiency plays a pivotal role. Energy production also plays a very significant role, and others criteria, the noise may be not so looked up upon, but the pollution and the CO2 emission is very important. And after processing all those things, you will come to the point that this is the final weightage of the alternatives. So for example, if you consider the grid and PV, so that is having the highest, almost highest weightage, and then the list is for the grid, PV and battery energy storage system, and then for the grid and all this PV, battery energy and CHPC system. So that depends upon the different, for all kinds of projects and planning, you may not have the similar results, but that depends upon the different aspects, different consideration, different objectives. So it changes with the objectives. Okay, so here the objective is different, and these are the reasons for that particular objective. Now, if you take the second example of the multi-criteria planning for the microgrid for the rural electrification. So according to the World Bank's World Development Indicators, about 85% of the world's households have access to the electricity, and still 15% do not have the access to the electricity. SSA or sub-Saharan African countries has the lowest energy access rates in the world, and roughly around 600 million people are still lacking electricity. And 13 countries in SSA have less than 25% access, compared to only one in the developing countries like in Asia. So these are the some 17 goals defined by the UN. And when we are discussing this kind of the things of distributed energy and microgrid and all those things, then mainly we are targeting this goal number SDG 7 and SDG 11. The SDG 7 is to provide affordable and clean energy, or the green energy, and the sustainable cities and commodities. So 11 is SDG 11 is not directly related to the generation, but it is indirectly related to the clean energy and affordable energy, because it includes the sustainable aspects, sustainable generation, sustainable living in the community and the society and the country. So cost of the energy is one of the most sensitive and the governing factors to decide the acceptance of the project by the price sensitive stakeholder or the local consumers. This objective is to highlight the fact that only the economic indicators are not sufficient to decide the overall success. The system under study is located in the Tanzania, and the objective was to make an electrification plan leveraging the multi-fold benefits of the microgrid. Why the particular site was selected? There are number of sites available which can be selected, but why it is selected, there are certain reasons behind that. It is a low income country. About 66% of the population lives in the rural areas. This particular site, Arusha, is selected. It's a city in the East Africa, Tanzania, is selected for the study. Irradiation level at the Tanzania, in particularly in Arusha, is about 6.17 kWh per meter square per day. Annual average wind velocity for the selected location is around 5.35 meter per second. And besides this, 10 kg of the biomass can produce 3 square meter of the biogas. So the site has sufficient amount of the availability of the biomass for the generation of the biogas and to drive the biogas based generator. It is for the rural remote region of the Tanzania, and approximately energy demand was 1,000 units per day. So this is the targeted demand. Again here, the comprehensive comparison has been presented using the Homer software and fuzzy analytic hierarchy process based multi-criteria decision making for planning of the isolated microgrid system. This is not a grid connected system, which is performed by using a group of the sources like PV, wind, micro, hydro, biogas based generation and battery energy storage system. In this study, 10 various alternatives comprising a blend of these sources have been considered, and at the end of the analysis, a levelized cost of $0.0694 per unit has been found for the optimized case using the Homer Pro, and it is comprising of the 5 aforementioned or the aforesaid components, meaning PV, wind, micro, and biogas, and the battery energy storage system. Okay, so basically it consists of this structure. It is under study as electric load, PV, wind, and all those things. And the principal characteristics are the 25 years of the project lifetime, 3% is the expected inflation rate, and 5% is the nominal discount rate. The different alternatives selected are, say for example, alternative A1 to A10. So A1 is PV plus wind, PV plus hydro, PV plus bio, PV plus wind plus hydro, PV wind battery energy, PV hydro battery energy, PV bio battery energy, PV wind hydro battery energy, PV wind bio battery energy, PV wind hydro bio and battery energy. So this 10th alternative that comprises of each and everything. So it is having PV, it is having wind, it is having hydro, it is having bio, it is having battery energy storage system. Whereas the other alternatives are lacking in one or other. If you look at some other aspects of that, then it is a composite nature of the load profile of a typical village is being considered, and it is having a population of around 2,500 to 3,000 people, and 1,000 units per day was the demand. Okay, so that is based on some of the studies carried out. The composite load includes what kind of the loads that it includes, because the energy demand is 1,000 units, and it is designed for around 2,500 to 3,000 people. So it includes the lights, fans, other typical domestic loads per households, water purifying system, many small industrial loads like cutting, sewing, grinding machines, healthcare system, school premises and associated loads. So some small kinds of the essential kinds of the loads are considered, being the rural pocket. And it is simulated in the Homer Pro to identify the group of energy sources that offer the most economic performance, and the list COE has been considered as a reference for the base system for the subsequent analysis. So what is being done in that particular case is, first this system is simulated on the Homer platform, and then the best system, some of the best system is again the data or the output from the Homer for that best system is given to the other algorithm, which is a fuzzy AHP base, fuzzy AHP, that is analytic hierarchy process based multi-criteria decision making system. So the components are, what kind of the components are being incorporated. So one is the generator, that is the generic biogas generator, which is 40 kilowatt on 1 unit. PV system is, there are 30 such units, each is of 325 watts, and such 1 unit is there. Storage system is a Gilmister, 10 kilowatt, 40 kWh. So it is 10 kilowatt into 5 units are there. Wind turbines, each wind turbine is 5.1 kilowatt, and there are such 4 turbines. And hydroelectric is Nettle free jet type of, and its capacity is 49 kilowatt, and 1 unit is being installed. So in this case, the analysis is carried out in this way. The first, the economic parameter are given more than 70% of the importance. So the economic aspects are given more weightage, leaving all other with the equal weightage. Then the second, all primary criteria are assigned equal weights. So all are given equal weights. And the third is expert opinions for the primary data are considered. And the opinions of the expert for the set of the primary criteria has been collected in the form of the scores based on the comparison of each other. So it is a comparison with A and B. So one criteria is compared with the second criteria. Similarly, one is compared with the third criteria, one is compared with the fourth criteria, one is compared with the fifth criteria, and similarly the second is compared with the third, second is not compared with the first one because it has already been done. So second is compared with the third, second is compared with the fourth, second is compared with the five, so on and so forth. Similarly, the third will not be compared with the first and second, but third will be compared with the fourth and fifth. So that kind of the data or the opinion is collected from the experts, and the experts are from the different setups, like one who is expert in the finance, one who is expert, group of experts who belong to the renewable, one who belongs to the environmentalist, and so on and so forth. So we can collect the different aspects. And a group of 15 members were asked to score the 5 primary criteria, and expert stakeholders, project planning, financing, designing, operating and maintenance, environment, protector, social welfare, workers, end user, electricity consumers, and the pairwise comparison is being done. So again, we'll not be going into this structural details. Then what is being done, a number is constructed from a set of scores assigned by the experts. The membership function is generated using the Jenks technique. Expert score close to the center are considered to have the more importance, and the weightage average of the center is estimated, and the relative distance is being matrix is being generated. Okay, and then at the end of this is all this after doing this computation, we have to find the consistency index. So whether whatever be the option or alternative we are suggesting is having a consistent in nature. Okay, so that consistency index is to be found out. Again, I am not going into the details of that consistency index and the randomized consistency index. So the competency of the CI can be validated determining the randomized index, and the consistency ratio is nothing but the ratio of the CI by RI, and based on that the cost of energy and net present cost of the microgrid system can be computed. So both this particular case, the microgrid is planned for the remote and rural application. The dispatch control strategy is the load flow following. Homer simulation results, the optimal alternatives are found to be 8 and. So this last one is found using the Homer simulation. Okay, using the Homer simulation, the last one is suggested to be the best one. Now, if we consider this the best one, then what would be the cost of the energy? That would be, as we had already discussed, that is 0.0694. The net present cost is this much, the operating cost is this much, initial investment, initial capital is this much dollars, renewable fraction is 100%. We haven't used any diesel, so renewable penetration is 100%. Total fuel being used is 19 point something liters. Annual worth is return on investment, internal rate of return, payback period is around 1.5 years, discounted simple payback period is around 1.77. So as you can see, it is having a very good, very short, simple payback period. So even less than 2 years, that break even would be reached. Based on that, these are the some results generated. Again, I'll not be going into this results. Then the sensitivity analysis is being carried out in the Homer. Wind turbine cost varies between plus or minus 10%. Biomass price is also varying plus or minus 10%. Generation genset cost is also varying plus or minus 10% within range of 20%. Genset lifetime is also varying with plus or minus 10%. Flow rate of the hydropower is also varying, but with minus of 10%. And hydropower plant cost is also varying with having plus or minus 10%. Okay, so such type of the sensitivity analysis is can also be carried out in Homer. If you look at the outcome of this, then the HPMC DM sits on the top of the generated results by the Homer Pro. Waterhead for the micro hydropower plant is the more impactful than variation of the other parameters. Then when all the primary criteria are given equal importance, when the expert scores are considered only the two renewable, that is PV and wind energy based generation, they are found most promising. And the similar analysis could be extended with the due modification for the grid connected microgrid plan. Okay, so this is very important aspect. Here it is being done for the independent isolated islanded system, but that can be even extended for the grid connected system. So, hybrids are the futures, was said by the Mike Bowen. And the Homer is being modeling the hybrid system for almost 30 years. It was started by NREL. Now they are focusing on the utility scale hybrids, time use arbitrage, grid connected microgrids for resilience, batteries for the demand charge management, and electric vehicles. So you can see the progress from the birth of the Homer, and in 1992 it was developed by the NREL. Now then they come to the Homer Energy, then Homer Pro, then Homer Grid, and then Homer Energy and Homer Front Plus UL analysis. So it basically consists of the project inputs. It requires economics, load profile, site-specific renewable sources, system components, analysis part. The simulation is done, so the runs each system for 1 year for every hour. Optimization identifies the most effective way to meet the electric load, and it uses its own proprietary derivative-free algorithm to search for the least costly system. Sensitive analysis can be done and what matters and when. So you can give the variation, the expected variation in the cost of the different things, span of the different things, etc. Results, economics and engineering, size, system sizing, performance details, financial different reports. I'll show some of the snaps later. So you can even download and try it for free for 21 days from this site. So basically it consists of 3 parts: input, analysis, and results, as I just mentioned in the previous one. Same thing is being discussed over here. Now, up till now, may I have any question, any doubts? Now, next 30 or 35 minutes, we'll be discussing on some of the snaps of the Homer. Those who are interested in working in that particular platform. So may I have any question till now?
Participants, if you have any query, you can ask, please. No query, sir.
Okay. So at least let me know some of the participants whether does it make any sense or it doesn't make any sense. So I can continue with some alteration or something like that. If it is not at all interested at all, or then we can quickly rush through the slides. And if someone finds interesting and if it makes some sense, then it would be that is the credit which I would like to have. Any comment, anything on this part? Does it make any sense? Whether it interests you or it doesn't interest you at all? So as I'm not getting any response from your side, any of the, I can see around 80 plus participants.
Participants are almost 100, but actually not a single question they are asking. Since morning I am observing it.
Yes,
but
yes.
This is the beauty of online sessions.
Yes.
Beauty
so you don't have any questions. So even if you don't know, if I don't know anything about, and if I present over here, then nobody would ask, and I'm not supposed to be afraid of answering, replying the questions which in fact I do not know.
There are so many participants from across the states, and I always encourage to ask the questions to directly expert, but still since morning not a single question are being asked.
See, in this such type of program, if I keep on telling and speaking and rushing through the slides, and it doesn't make any sense. Everything you can get from the website. The links are given. Everything can be accessed. So there is no meaning in discuss without any discussion or without any interaction. What I guess is.
Yes, sir.
I'm leaving to you all the participants, as I'm given an opportunity to discuss those things. I'll have to. It's my duty to serve those things. So even later on, also you can have any query. You can route it through Dr. Ashutosh or directly to me. I would rather be more happy to answer your queries if there. So let's continue, because it is almost 5:05 and I also joined 10-12 minutes late. So my apology for that, but anyway, let's continue. So this is
no issue.
That is because why I'm asking, say in such any application software, the beginning is difficult. Once you understand some basics or the fundamental things of handling that any of the softwares, any of the application softwares, then you can play around easily. So that's why I'm asking this questions to the participants. Anyway, so this is the same thing which we had already discussed. So that consists of some electrical load, then the PV installation, then battery, then converter, then biogas based generation, then you have a hydro, small, even not small, even it is a mini micro hydel power plant, and a small wind turbine. So each wind turbine is 5.1 kilowatt, and there are such 4 turbines available. There is only 149 kilowatt mini hydro turbine is there. I've just taken the snap from the same study, so you can duplicate, you can replicate using the same data. So discount rate, inflation rate, annual capacity shortage. I have not taken into account. Project lifetime is 25 years. Second is the generic biogas genset, and the capacity is 15 kilowatt. The capital cost would be around 6,000. Replacement is taken as 2,500. Operation and maintenance cost is 0.1. The numbers are not chosen hypothetically. The numbers are chosen based on some literature, some availability of this particular kind of the product on the market, and based on that these numbers are selected. So these are not randomly or assumed numbers. So that's why I'm trying to emphasize on that, because what happens when you simulate design and simulate the system without feeding appropriate number, what is commonly known as the garbage in and garbage out. So if the numbers are not appropriately fed in, then you will be getting the absolutely incorrect results, absolutely incorrect outcomes. And it may be possible the project is viable, but at the end of your analysis, you will say that the project is not physically feasible or viable. So that's why there are certain important points or the numbers which we should keep into mind. A minimum load ratio is taken as 50%. Minimum run time in minutes is 50%. So it means that the downtime can be 15 minutes, and after the 15 minutes, the system can be restarted. The lifetime in hours is chosen to be 20,000, and the different such space is taken as 40, 45, and 50 kilowatts. Okay, so it is a 15 kilowatt system, but you can go for up to 40, 45, and 50 kilowatt. Heating value of the fuel that is being used here, it is a biomass, so it is around 18 mj per kg, megajoule per kg. Density is 1.15. Carbon content is around 5%. There is no sulfur content included. Second source is the hydro. And in that, the capital cost, obviously the capital cost has to be very high. That is the 2,50,000. The currency is in dollars, US dollars. Replacement cost is also comparatively higher. Operation and maintenance cost is also higher, but the lifetime is 30 years. And it is connected with the AC bus. The pipe head loss, those who have some idea about the hydropower system, the pipe head loss is around 15% is to be taken. Available head is 70 meters. So please be careful. It is a mini micro hydral kind of a system, and hence the head is not in terms of 300 feet or 340 feet or something like that, but it is a 7 meters. So 7 meters is almost around 7 threes are 20 or something like that. So it is around 20-25 feet of height. Design flow rate is also not very high, very large. It is 1200 liters per second. Minimum flow rate is 21 point something, and maximum flow rate is around percentage is 105. And efficiency of this system is 59.52%. Similarly, if we keep on continue, then the wind turbine is cost is this is for 5.1 kilowatt turbine, and approximate cost is 6,000. Replacement is 2,400. Operation maintenance is taken to be 20. Search space is 4, 6, and 8. And as you can see, for the different wind speeds at the 2.2 meter per second, it would generate this much output. 2.7, it would be having this. 3.1, it would be having this. And at the rated, it would be having this much amount of the power. So at the 12 meter per second, it would be having around 5.1 kilowatt of output power. So you can say that the operating range is around 5 meter per second to 12 meter per second. So the cut-in and cut-off speed you can consider from this point. Lifetime is 20 years, and the hub height is 12 meters. So it is not too tall. It is 12 meters height because it is a small size wind turbine. It is not a very large size wind turbine, which is having typical capacity of around 6 megawatt or even 9 megawatt, and 10 megawatts are under the research. So it is a very small wind turbine, 5.1 kilowatt turbine, and there are 4 such turbines are there, and that's why this quantity is 4. So you can have 4 turbines, 6 turbines, and 8 turbines. Then the load profile would look something like this. As you can see over here, it is a residential load profile, and hence it is having a double hump kind of a shape. Average load is in kWh per day is 850. Average kilowatt is around 35 point something. Peak load is 125, and load factor is around 0.28. So here you have to supply the load profile to the system, and that's why I have listed out what are the inputs, then what is the simulation, and then what is the analysis. So here the efficiency multiplier is 1, capital cost is 0, the lifetime of the project is 25, and annual scale average is 850 units per day. Converter is fine. It is a very small converter, and which is connected between the AC bus and the DC bus, just to take care about the power generated from the PV and the battery stored energy. So it is a 1 kilowatt and $200 replacement could be the different one. If you select the higher size, the difference replacement could be different. Lifetime is 15 years. Generally, the converter life is much less than the project life. So it could be 10 years, it could be 5 years, it could be 15 years, but not more than 20-25 years. Efficiency is 95%. And the efficiency of the rectifier inverter, both are taken to be 95%. And the most fascinating and important is the solar photovoltaic module. So here the Canadian solar module is being used. Typically it offers 325 watts. So the total capacity is 40 kilowatt, and the capital investment is around $60,000. Replacement would be around $15,000. Maintenance would be cleaning, etc. That includes the $200 per year. Lifetime is 25. Again, the search space is 30, 40, and 50. And the D rating factor is considered to be the 88. You can consider the D rating factor different as per the manufacturer's suggestions. So here it is temperature coefficient, everything is been mentioned, and you can even cross verify with the manufacturer's website. Such space is taken as 20 and 30, so it can go for even 20 kilowatt, it can go for even 30 kilowatt, but the rated capacity is 40 kilowatt. Similarly, for the storage unit, it is one storage unit, it could be 3 storage unit, could be 4, and could be 5 storage units. And each storage unit, each quantity, each is costing $5,000. Replacement is comparatively almost 50%. The time of the battery is 10 years, and the throughput of the battery is 876,000. Nominal voltage is 40, nominal capacity is 40 kWh. If you convert it into ampere hour, then it is 833. Round trip efficiency is 64%. Charge current is 200, and discharge current is 13 amperes. Okay, it is a 48 volt battery. Initial state of charge you can supply, that is 95%. Minimum state of charge you can also supply, that is 20, and minimum storage life is around 5 years. Minimum storage life is around 5 years, but it can last up to 10 years. So these are the values for for the system of the Tanzania, Arusha. The second one analysis was done for academic institutions, and the actual load profile is being taken. So that actual load profile looks something like this. This is captured using the fluke analyzer. And as the academic institution may not be having the biogas and wind and all those things, so only the diesel generator, photovoltaic and storage elements are connected, battery energy storage elements are connected for these values. So the discount rate is 6%, inflation is 2%, annual shortage is, there is no annual shortage, and project lifetime is 25%. So that actual load profile is altered, which is for the academic institution, is now altered for the different categories. Like we are keeping the annual consumption of energy same as that particular institution. How the profile of for the commercial would look like, how the profile for the industrial would look like, for the community would look like. So there are 3 different profiles were extracted for the different seasons or the different months based on the average daily profile. So it is for the dotted is for May, and the second one is for the December. So there are different profiles. In December, the load is less. The load is more in the months of the summer, like April, May, June, and something like that. So here in this case, the peak load is for the academic, residential, commercial, industrial, and community kind of the setups are given. We have considered the average demand is 1030 units per day. Average kilowatt is 43. Time step is 60. Day to day is 5%, and time step is also 5%. So based on that, you can get the yearly profile as this much. And this is derived from the annual electricity consumption from the utility. So as I have already mentioned that the different profiles are being extracted. So this is for the daily profile, equivalent daily profile for the residential kind of the load. This is for the community type of the load. This is for the commercial type of load, and this is for the small and medium industry kind of a load. So the only thing is the average energy demand and average kilowatt remains unchanged for all kinds of the setups, and based on their nature they are customized. So here also as you can see the setup, how the panels are set up. So there are 75 kilowatt rooftop PV system, and there are 3 inverters and 325 multicrystalline silicon 325 watt multicrystalline silicon panels. 230 such panels were installed, and based on the place, the irradiation and solar irradiation, the clearness index is being captured. And for this 325P module, The rated efficiency is 16.94, and the capital cost and everything is being mentioned over here. Similarly, this is a property for the storage battery system. So again, here also it is a Guildmeister and FP 1070. So the 10 kilowatt and 70 kWh system is being used. The nominal capacity is 1460. And this is actual electricity generation for the 75 kilowatt rooftop PV system. So as you can see, in the month of May, it is this much. Then in July, it drops, and it is picking up in month of the August and so on. And in October, it is the highest. Then November, it is again reducing, and then it is almost equal in the months of the December, January, February, and again March, it is slightly more, and April, it is 1.4 and something like that. So these are some of the properties of the diesel generator. Diesel generators are meant for the emergency or the backup purpose, and it is not run throughout the working hours of the institute and so on and so forth. The properties of the utility grid is also taken. How many units are being purchased during that particular time frame? What is the minimum or the average outage per year? What is the minimum repair time or restoration time? Repair time variation is the 25%. There are different tariff structures chosen. So for 6 to 5, 5 to 10, and 10 to morning 6, the different tariff structures are chosen. And based on that, these are the results generated. So we'll not be going into all the results, but we'll be discussing some critical points. So it is without the grid cell, when the academic institute is not selling to the grid, and with the grid cell, I mean the grid cell meaning that we are getting the feed-in tariff, and tariff and the feed-in tariff. So if we are feeding surplus power into the grid, then what would be the statistics? And if you do not sell the power to the grid, then what would be the statistics? So here you can see the return on investment. These are the financial parameters which most of the investors are interested in this. So return on investment for the different categories: academic, residential, commercial, community, and industrial. For case when there is no energy is being sold to the grid, and when some amount of the power or the energy is being sold to the grid. So as you can see, the simple payback period is around 3.8, 2.2 years, and here for the commercial it is very high, and for the community also it is very high. So that depends upon the profile of the load, the profile of the, irrespective of whether the surplus energy is being sold to the grid or not. Okay, so these are the same kind of the results are being generated over here in place. So here the same kind of the panel is being utilized. Only the difference is the battery may be different as per your requirement. And if you look at the results generated, so the result, there are two results being generated. One is for 1000 kilowatt hour per day, and the other is 950 kilowatt hour per day. So if we take the most optimized one, then it is for, say, for example, the one is, say, for 1000 kilowatt hour per day. Then if we go into the detail of that analysis, then this would be generated. So that gives you the classification based on the component. So it is for, if the wind turbine was used, in case of the Arusha and wind turbine was used, then the capital cost was this much, replacement, operation, maintenance, fuel cost, and the total cost would be this much. Canadian Solar, this particular analysis for the Arusha case, Tanzania Arusha case, where all kind of the sources are being used, almost all kinds of sources are being used. The case what we had discussed is for the academic case, and in that case only the only the photovoltaic, rooftop photovoltaic is being installed with the battery, and for the emergency cases or the backup power, the diesel generators are being used. So that this analysis is pertaining to the Arusha case. So please mind well, don't get confused with this analysis and the previously discussed case. That is for your understanding, and this is for the Homer understanding. So there are different components. Each component's capital cost are given, replacement cost, operation maintenance, fuel cost, salvage cost, and total cost are given, and the system cost is this much are the system costs. Okay, so it includes each and everything. Then you can even get the picture by the cost type. So what would be the contribution of the capital cost, what would be the cost in the operating, what would be the contribution in the replacement, what would be the salvage, and what would be the fuel cost. So here if you compare the economics, then the base system is being compared with the current system. So base system and the current system, you will get the values of the present. What would be around, if you convert in terms of the rupees, then 4974. Then annual worth would be, this return on investment is very high. It is very attractive. That is 76.6%. Internal rate of return is also very good. That is 61%. Payback is very less. That is 1.6, and discounted payback is 1.77. If you look at the electrical aspects only, then the primary load, what is the primary load? We do not have any DC load, so the primary load is around this much, and 100% AC load, and is scattered by the system, and the system consisting of the solar photovoltaic, biogas, wind, hydro, and the total would be this much. So we have generated this much amount of the energy, we require this much amount of the energy, and the excess is this much. 71 units are the excess units. So unmet electrical load is 132 units per year. Capacity shortage is 352 or something like that. Renewable fraction is around this, and renewable penetration is this value. So this is something about the Homer, and I would also like to show the actual simulation, but it would take some more time, and we are also already running out of time.
Yes, sir.
And some of the participants are also not showing their much interest.
They have asked some question. Dr. Ami madam will